Black holes might be the universe's greatest lie. For a century we've been taught that when the most massive stars die, they collapse into objects so dense, so absolute, that nothing can escape. Event horizons, singularities, infinity compressed into a point smaller than an atom. We've built entire branches of physics around these monsters, detected their gravitational waves, photographed their shadows, and declared the case closed. But what if the universe found a loophole? What if there's something out there that looks like a black hole, acts like a black hole, pulls with the same crushing gravity but refuses to play by the same rules? What if instead of collapsing into nothingness, dying stars create something even stranger? They're called gravastars, and if they exist, they rewrite everything. No singularity, no event horizon, no infinite density hiding behind a cosmic curtain. Instead, a thin shell of matter so exotic, under pressure so extreme it exceeds 10 to the 45 Pascals, that it holds back total gravitational collapse through sheer force of will. Inside that shell, not a point of infinite destruction, but a bubble of dark energy, quiet and stable, defying every instinct physics has about what happens when mass runs out of options. Outside, gravitational forces so violent they could rip apart anything within millions of miles, not because of what falls in, but because of what refuses to. In 2001, two physicists proposed this idea, and the community mostly ignored it. Too strange, too convenient, too much like science fiction wearing equations as a disguise. But in the decades since, the math has held. The models have evolved. And now, as our telescopes grow sharper and our gravitational wave detectors grow more sensitive, we're faced with a question no one wanted to ask. What if some of the black holes we've been studying aren't black holes at all? Welcome to Space Dust. If you're new here, please subscribe. We make these documentaries every day and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. We begin with something that used to be simple. A massive star runs out of fuel. The outward pressure from fusion that has held the star up for millions of years vanishes. Gravity wins, the core collapses, and what remains, once the star has finished dying, is a black hole. Event horizon, singularity, done. That story has been gospel for more than half a century. It sits in every introductory astrophysics textbook, every documentary, every conversation about the fate of massive stars. The narrative is clean, it's elegant. And according to general relativity, the theory that has guided our understanding of gravity since 1915, it is exactly what the math predicts. A sufficiently massive star that exhausts its nuclear fuel has nowhere to go but down. Collapse is inevitable. The equations march forward with brutal certainty. First the core compresses, then the density climbs, then the space-time curvature becomes so steep that not even light can escape. An event horizon forms, and beneath that horizon, hidden forever from the rest of the universe, the collapsing matter continues inward until it reaches a point of infinite density and infinite curvature. A singularity. The endpoint of collapse. The place where the math stops working and the universe, for lack of a better word, breaks. That is the standard story. And for decades, physicists have been staring at that story and quietly, politely, admitting that something about it makes them deeply uncomfortable. Not because the observations are wrong. We have seen black holes. We have imaged the shadow of one at the centre of Messier 87, a supergiant elliptical galaxy 55 million light-years away. We have detected gravitational waves from black hole mergers, events so violent they ripple space-time itself across billions of light-years. The evidence for objects that behave like black holes is overwhelming. The problem is not the observations. The problem is what happens at the end. The singularity. That word singularity is a polite way of saying the theory has given up. When a physical model predicts infinite values, infinite density, infinite curvature, what it is actually saying is this: I do not know what happens here. The equations break, the predictions become meaningless. You have reached the edge of the map, and beyond this point here be dragons. General relativity, the most successful theory of gravity ever constructed, predicts its own failure at the centre of every black hole. That is not a minor footnote. That is a flashing red warning light built into the foundation of modern cosmology. and it has been flashing since the moment physicists first worked out what the equations were saying. In 1916, just months after Einstein published his field equations, Carl Schwarzschild found the first exact solution describing the space-time around a spherical mass. He did it while serving on the Russian front in World War I, solving Einstein's equations in the trenches between artillery barrages. The solution he found described a point mass, and it contained two features that would haunt physics for the next century: a radius where the geometry became infinitely curved, and a boundary where time itself appeared to stop. Schwarzschild died of an autoimmune disease later that year, and his solution sat in the literature like a ticking bomb. For decades, physicists assumed the singularity was a mathematical artifact, something that would go away once you accounted for rotation or asymmetry or some other real-world complication. Stars are not perfect spheres. Collapse is not perfectly symmetric. Surely they thought nature would find a way around the infinity problem. Then in the 1960s, Roger Penrose and Stephen Hawking proved otherwise. They showed, using rigorous mathematical theorems, that singularities are not accidents. They are generic. Under very general conditions, if you have enough mass in a small enough region, collapse to a singularity is unavoidable. You cannot rotate your way out. You cannot add pressure. You cannot appeal to a symmetry. The singularity theorems, as they came to be known, closed the escape hatches one by one. If general relativity is correct, and if the collapse proceeds without interference, then the formation of a singularity is not just likely, it is guaranteed. That conclusion earned Penrose half of the 2020 Nobel Prize in Physics, and it left the field with a problem it has never fully solved. Because if singularities are real, then general relativity is incomplete. A theory that predicts its own breakdown is not the final word. It is a placeholder, waiting for something deeper. Most physicists assume that something deeper will be a quantum theory of gravity, a framework that unifies general relativity with quantum mechanics and smooths out the singularity before the density goes infinite. But we do not have that theory yet. We have candidates. String theory, loop quantum gravity, a dozen other approaches. But none of them have made testable predictions we can check against observation. We are flying blind. So here is where we stand. General relativity says massive stars collapse into black holes. Black holes contain singularities. Singularities are places where the theory fails. And until we have a working quantum theory of gravity, we cannot say with certainty what actually happens at the centre of a black hole. That uncertainty has been sitting in the background of astrophysics for more than 60 years. Most of the time, it gets ignored. Black holes work well enough as a model. The event horizon hides the singularity from view, so whatever weirdness is happening inside does not affect the rest of the universe. Out of sight, out of mind. But ignoring a problem does not make it go away. And over the last 2 decades, that ignored problem has started causing real trouble in a completely different area of physics. Quantum mechanics. The trouble has a name, the black hole information paradox. And it goes like this. In quantum mechanics, information is never destroyed. If you know the exact state of a system at one moment, the laws of physics allow you to predict its state at any future moment and reconstruct its state at any past moment. This property is called unitarity, and it is one of the foundational principles of quantum theory. Break unitarity and you break the entire framework. Particles would start behaving unpredictably, conservation laws would fail, the universe would stop making sense. Now consider a black hole. You throw a book into it. The book crosses the event horizon and falls toward the singularity. The information contained in that book, the specific arrangement of every atom, every quantum state, is now inside the black hole. From the outside, you can measure the black hole's mass, charge, and spin. That is it. Everything else about the book is hidden. The black hole has no hair, as the saying goes. It does not remember what fell in. That alone is troubling, but it gets worse. In 1974, Stephen Hawking showed that black holes are not perfectly black. They emit radiation. Quantum effects near the event horizon allow particle-antiparticle pairs to form, with one particle escaping and the other falling in. Over enormous timescales, this Hawking radiation causes the black hole to lose mass. Eventually, the black hole evaporates completely, and when it does, the information that fell in, the book, the atoms, the quantum states, is gone, destroyed. Unitarity violated. That is the paradox. General relativity says the information is lost. Quantum mechanics says it cannot be. Both theories are extraordinarily successful in their respective domains, and they are giving contradictory answers to the same question. For nearly 50 years, physicists have been trying to resolve this. Some argue the information is somehow encoded in the Hawking radiation, smuggled out in correlations too subtle to detect with current methods. Others propose the information is stored at the event horizon itself, holographically imprinted on the surface. A few have suggested the paradox is telling us that black holes do not actually have event horizons, that something prevents the horizon from forming in the first place. That last idea, the idea that black holes might not be black holes in the traditional sense, used to be fringe. It was the kind of thing you could propose in a speculative paper and watch your colleagues politely avoid eye contact at conferences. But the information paradox has not gone away. If anything, it has gotten sharper. And as the contradictions pile up, a growing number of physicists have started asking a question that used to be unthinkable. What if the standard story is wrong? What if stellar collapse does not always end in a singularity? What if massive stars have another option? Think about what that would mean. Every time we detect gravitational waves from a merger, every time we image the shadow of a supermassive black hole, we assume we are looking at an object with an event horizon and a singularity at its core. That assumption is baked into the models we use to interpret the data. If the assumption is wrong, if some or all of those objects are something else, then we have been misidentifying the most extreme objects in the universe for decades. The observations would still be real. The masses would still be there. The gravitational effects would still match the predictions. But the interior, the hidden engine driving all of it, would be fundamentally different. Not a bottomless pit where information goes to die, something stranger, something that obeys different rules. This is not idle speculation. There are serious peer-reviewed proposals in the physics literature describing compact objects that could mimic black holes from the outside while avoiding singularities and event horizons on the inside. These proposals have names: fuzzballs, firewalls, Planck stars, and the one we are going to focus on, the one that has been gaining traction as both a mathematical curiosity and a potential astrophysical reality, gravastars. The term is short for gravitational vacuum star, and it was introduced in 2001 by physicists Pavel Mazur and Emil Mottola in a paper that proposed a radical alternative to the black hole endpoint. Their idea was simple in concept, bewildering in execution. What if the final stage of collapse is not a singularity but a phase transition? What if the interior of the collapsing star does not continue shrinking forever, but instead transitions into a different state of space-time, one with no singularity, no event horizon, and no information paradox? The paper described an object with 3 layers. An outer shell of normal matter, a thin intermediate shell under extreme tension, and an interior filled with something that looks, mathematically, like the opposite of a black hole. Instead of a region where gravity pulls everything inward, the core would be a region where a kind of negative pressure pushes outward. The technical term for that negative pressure is dark energy, the same mysterious force that is currently accelerating the expansion of the entire universe. In a gravastar, that force would be concentrated in a tiny region, compressed to pressures so extreme they make the center of a neutron star look like a gentle breeze, 10 to the power of 45 Pascals. A number so large it loses meaning outside the context of equations, but the result of all that pressure would be stability. The dark energy core pushes out, the outer shell pushes in, the forces balance, and instead of collapsing to a singularity, the star settles into a new equilibrium. Compact, dense, but not infinite. No singularity, no information loss, no paradox. When Mazur and Mottola published their proposal, the reaction was mixed. Some physicists dismissed it as exotic speculation, too far removed from known physics to take seriously. Others were intrigued. The gravastar model used only general relativity, no string theory, no quantum gravity, just Einstein's equations applied in a different way, with a different assumption about what happens at the endpoint of collapse. The math worked. The solution was stable, and crucially, from the outside, a gravastar would look almost identical to a black hole. Same mass, same gravitational field, same light-bending effects. If you replaced every black hole in the universe with a gravastar, most astronomical observations would not change at all. The differences would only show up in subtle effects near the surface, effects we do not yet have the instruments to measure. That observational degeneracy is both the model's strength and its weakness. It means gravastars cannot be ruled out by existing data. But it also means they cannot be confirmed. The idea did not catch fire immediately. For most of the 2000s, gravastars remained a niche topic, cited occasionally in papers exploring alternatives to black holes, but not seriously considered as a mainstream explanation for astrophysical observations. Then, the detection started coming in. In 2015, LIGO detected gravitational waves from the merger of two black hole candidates, each weighing dozens of solar masses. The signal matched the predictions of general relativity with extraordinary precision. The masses, the spins, the ring-down frequency after the merger, everything fit. But here is the thing. The signal also fit the predictions for a gravastar merger. The differences between the two scenarios are small, buried in the fine details of the waveform. With the sensitivity of early LIGO, those details were lost in the noise. The detections proved we are observing compact objects with event horizons, or something that behaves almost exactly like an event horizon. They did not prove what is inside. Since then, the field has detected more than 90 gravitational wave events, black hole mergers, neutron star mergers, mixed events. Every detection refines the models and tightens the constraints. And so far, every detection is consistent with the black hole interpretation. But every detection is also consistent with alternatives. As long as the alternative mimics a black hole closely enough, the data cannot distinguish between them. That ambiguity is maddening to some physicists and tantalizing to others. It leaves the door open, not wide open, but ajar. Enough to let in the possibility that the universe is hiding something from us. The gravastar model forces us to confront an uncomfortable truth. We have never observed the interior of a black hole. We have never seen a singularity. We have never directly confirmed that event horizons exist. What we have observed are objects that behave the way general relativity says black holes should behave. That is not the same thing. The difference matters. If black holes are exactly what the textbooks say, then we are looking at the universe's most extreme proof that general relativity works all the way down to the smallest scales. If they are not, if they are gravastars or some other exotic compact object, then the story is more complicated, and the universe, as it turns out, loves complications. The standard black hole narrative has one other problem, and it is worth naming explicitly. The singularity is not just a place where the math breaks, it is a place where causality, the idea that cause precedes effect, stops making sense. Inside the event horizon, all paths lead inward. You cannot stop. You cannot turn around. You cannot stay still. The geometry of space-time itself drags you toward the singularity, and once you cross the horizon, reaching the center is not a choice. It is as inevitable as reaching next Tuesday. That is what the math says. But what happens when you get there? General relativity does not answer. It cannot. The singularity is a boundary where the theory gives up, shrugs, and walks away. If that does not bother you, it should. Because a theory that describes the universe but cannot describe what happens at the most extreme point the universe allows is not a complete theory. It is a very good approximation with a hole in the middle. The gravastar model, and others like it, are attempts to fill that hole, not with wishful thinking, but with physics. The claim is not that black holes are wrong. The claim is that the endpoint of collapse might be more nuanced than the simplest models predict. That when you account for quantum effects or phase transitions or exotic matter states we have not yet observed in a lab, the singularity might be avoided. The collapse might terminate in something stable, something real, something that does not require infinity. And if that is true, then everything we think we know about the final fate of massive stars is incomplete at best and misleading at worst. Here is the central question, the one that drives the rest of this story. What if the universe does not allow singularities? What if, at the moment of ultimate collapse, something intervenes? Not a miracle, not a violation of physics, just a mechanism we have not accounted for, operating at scales and energies we have never tested. What if massive stars, when they die, do not disappear behind an event horizon and collapse to a point of infinite density? What if they cheat death? What if they settle into something else, something stable, something that solves the singularity problem and the information paradox in one stroke? That is the possibility we're going to explore. Not as science fiction, not as speculation for its own sake, but as a serious, mathematically grounded alternative to the story we have been telling for more than half a century, the story of black holes. And if that alternative is real, if gravastars or objects like them actually exist, then the universe is hiding its most dangerous secret in plain sight. We have been looking at them for years. We have been cataloguing them. We have been measuring their masses and spins and calling them black holes. And all along, they might have been something else. Something without a singularity. Something without an event horizon. Something that makes black holes, those lightless pits we thought were the most extreme objects in existence, look almost safe by comparison. That is where we are headed. Into the mathematics of objects that should not exist, held together by forces we barely understand, sitting at the edge of what general relativity allows, objects that rewrite the ending of stellar collapse and force us to ask whether we have ever truly understood what happens when a star dies. The standard story is about to get complicated, and the complications, as always, are where the truth hides. The idea that would become the gravastar was born in a moment of intellectual frustration. Pavel Mazur, a physicist working at the University of South Carolina, had spent years thinking about the endpoint of gravitational collapse, and the more he thought about it, the less sense the standard picture made. Black holes were mathematically elegant, they fit the observations, but they required you to accept something that no working physicist should ever be comfortable accepting: infinity, infinite density at the singularity, infinite curvature, the equations marching toward a value that meant the theory had broken down. And lurking behind that breakdown was the information paradox, the unsolved contradiction between general relativity and quantum mechanics that had been festering since Hawking's work in the 1970s. Mazur was not alone in his discomfort. Plenty of physicists had raised similar concerns over the years, but most of them assumed the solution would come from quantum gravity, some future theory that would smooth out the singularity at scales smaller than the Planck length, about 10 to the minus 35 meters. The problem was that no one had that theory yet. String theory was still a work in progress. Loop quantum gravity had not made testable predictions. And in the meantime, the singularity sat there in the equations, unresolved, a placeholder for physics we did not understand. Mazur took a different approach. Instead of waiting for quantum gravity, he asked whether general relativity itself, the same theory that predicted the singularity, might also contain the tools to avoid it. The key, he realized, was to stop thinking of collapse as a one-way trip to infinite density and start thinking of it as a process that could be interrupted. Not by exotic new physics, but by a phase transition. A sudden change in the state of the matter, the way water turns to ice when the temperature drops below freezing. If the collapsing core of a massive star could undergo a phase transition at just the right moment, it might settle into a new stable configuration. No singularity, no information loss, just a different kind of equilibrium. That insight formed the core of the Gravastar proposal. But turning an insight into a working model required more than intuition. It required mathematics, careful construction, and a willingness to follow the equations into territory that most physicists considered off-limits. Mazur partnered with Emil Mottola, a theoretical physicist at Los Alamos National Laboratory, and together they began building the framework. The result was a preprint posted to the archive on September 11, 2001. The timing was coincidental, but the title was deliberate. Gravitational Condensate Stars, an Alternative to Black Holes. The word gravastar appeared in the abstract, a contraction of gravitational vacuum star, and it described an object that had never been observed, never been detected, and according to the conventional wisdom of the time should not exist. The proposal was radical, but not reckless. Mazur and Mottola were not throwing out general relativity. They were working within it, using solutions to Einstein's field equations that had been known for decades but rarely applied to the problem of stellar collapse. The key was to recognize that general relativity allows for more than one kind of space-time geometry. The Schwarzschild solution, the one that describes black holes, is the most famous. But there are others, and one of those others, called de Sitter space, describes a region where the geometry is dominated not by mass pulling inward, but by a kind of outward pressure, a negative pressure, technically, the same kind of effect that is driving the accelerated expansion of the universe today. De Sitter space shows up in cosmology all the time. It is the geometry you get when dark energy dominates, when empty space itself pushes things apart rather than pulling them together. What Mazur and Mottola proposed was to take that cosmological geometry and shrink it down to the size of a collapsing star. Instead of a singularity at the centre, you would have a core made of something that behaves like dark energy. A region where space-time itself is in a different phase, a gravitational vacuum condensate, pushing outward with enormous pressure. That pressure would counterbalance the inward pull of gravity, and the collapse would halt. Not at infinite density, but at a finite, stable configuration. The structure they described had 3 layers. The innermost region, the core, would be a patch of de Sitter geometry. Uniform static, no singularity. The outermost region, far from the object, would look like normal Schwarzschild geometry, indistinguishable from the space-time around a black hole. And in between, connecting the two, would be a thin shell, a boundary layer where the transition happens. That shell is where the Gravastar model gets strange, because the transition from one geometry to another is not smooth. It happens abruptly, across a surface that has to support an enormous amount of tension to keep the interior and exterior geometries from collapsing into each other. The shell has to be thin, rigid, and under more stress than any material we have ever observed in nature. Mazur and Mottola modelled that shell as a pair of spherical surfaces with vanishing energy density but non-zero surface pressure. In other words, the shell has no mass, but it pushes, hard. The pressure required to stabilise the structure is so extreme that it makes the core of a neutron star, where atomic nuclei are crushed into a soup of quarks and gluons, look gentle by comparison. We're talking about pressures in the range of 10 to the power of 45 pascals. To put that in perspective, the pressure at the centre of the Earth is about 360 gigapascals. The pressure inside a neutron star core is somewhere around 10 to the power of 34 pascals. The Gravastar shell is 10 billion times more extreme than that. It is a number that stops making physical sense in any everyday context, but mathematically it works. The equations balance. The structure is stable. That stability is the whole point. A Gravastar, if it exists, does not collapse further. It does not radiate away its mass and evaporate like a black hole would over incomprehensible timescales via Hawking radiation. It just sits there, holding itself up with a combination of internal pressure from the de Sitter core and tension in the shell. From the outside, you would see an object with a mass, a radius, and a gravitational field almost identical to a black hole. The differences would only show up close to the surface, in the details of how light bends and how matter behaves near the boundary. And because that boundary is not an event horizon, light can still escape from it. Barely. The surface of a Gravastar would be extraordinarily redshifted, meaning light climbing out of the gravitational well would lose most of its energy on the way up. But it would not be trapped. There is no one-way membrane, no point of no return. Information can get out. That last detail is what makes the Gravastar model appealing as a solution to the information paradox. If black holes have event horizons, then information that crosses the horizon is lost to the outside universe, at least until the black hole evaporates. And when it evaporates, the information is either destroyed, violating quantum mechanics, or encoded in the Hawking radiation in a way no one has been able to demonstrate convincingly. Gravastars sidestep the entire problem. There is no horizon. The information never gets trapped. Whatever falls onto the surface of a Gravastar can in principle be retrieved later. Quantum mechanics is preserved. The paradox evaporates. Of course, there is a cost. The cost is that you have to accept the existence of a phase transition that has never been observed, and a shell under pressures that no known material could sustain. That is a steep price. But for Mazur and Mottola, it was a price worth paying if it meant avoiding the singularity and the paradoxes that come with it. Their model was not a proof that Gravastars exist. It was a proof of concept, a demonstration that general relativity allows for stable, non-singular endpoints to gravitational collapse. Whether nature actually takes advantage of that possibility is a different question. The reaction to the Gravastar proposal was mixed, which is a polite way of saying most physicists ignored it, and a few dismissed it outright. The criticisms were predictable. The model relied on exotic matter, a phase transition with no known physical mechanism and pressures far beyond anything we could test in a laboratory. It was mathematically consistent, but physically speculative. And in a field where speculation is cheap and observations are expensive, speculation without a clear path to testability does not get much traction. Some critics pointed out that the shell, with its extreme tension and vanishing energy density, looked suspiciously like a delta function, a mathematical abstraction rather than a physical object. Others noted that even if the phase transition could happen, there was no reason to expect it would happen at exactly the right moment during collapse to produce a stable gravastar rather than continuing onward to a singularity. But the most common criticism was simpler. We already have a model that works. Black holes explain the observations, they fit the data. Why complicate things with an alternative that makes the same predictions but requires more assumptions? It is a fair point, and it reflects a deeper tension in theoretical physics between parsimony and completeness. Occam's razor tells you to prefer the simplest explanation. But what do you do when the simplest explanation has a gaping hole in the middle? A singularity where the theory admits it cannot describe what happens? Do you stick with the simple model and hope the hole gets filled later? Or do you explore alternatives that avoid the hole, even if those alternatives require ingredients that have not been observed? Mazur and Mottola bet on the second option. And while their proposal did not trigger a revolution, it did something more subtle. It opened a door. It demonstrated that the black hole endpoint was not the only possibility on the table. Other researchers, intrigued by the idea of avoiding singularities, began exploring related models. Some proposed variations on the gravastar structure, tweaking the shell or the core geometry to make the model more physically plausible. Others explored whether quantum effects near the collapsing core could trigger the phase transition Mazur and Mottola had invoked. The gravastar became part of a broader conversation about what happens at the endpoint of collapse, a conversation that included fuzzballs, firewalls, Planck stars, and half a dozen other exotic proposals. That conversation gained urgency in the years following the original gravastar paper. In 2004, the gravastar model was cited in a paper published in the Proceedings of the National Academy of Sciences, a sign that the idea was being taken seriously enough to warrant discussion in a mainstream venue. Around the same time, other physicists began revisiting the question of whether black holes could be replaced with horizon-free objects that mimic black hole behavior from a distance. The information paradox had not gone away. If anything, it had sharpened. Hawking himself, in 2004, made headlines by reversing his earlier position and suggesting that black holes might not destroy information after all. He did not provide a mechanism. He just acknowledged that the paradox was forcing physicists to reconsider assumptions that had seemed solid for decades. The gravastar fit naturally into that reconsideration. It was not the only alternative, but it was one of the few that stayed within the framework of general relativity rather than appealing to speculative quantum gravity effects. That made it easier to analyze, easier to criticize, and easier to compare against observations. And as gravitational wave detectors came online in the 2010s, the possibility of testing the gravastar hypothesis started to look more realistic. If you could measure the merger of two compact objects with enough precision, you might be able to distinguish between a black hole merger and a gravastar merger. The differences would be small, buried in the fine details of the waveform, but they would be there. The central claim of the gravastar model is that the phase transition happens at a specific point during collapse, just before the event horizon would form. The collapsing matter reaches a critical density, the space-time geometry becomes unstable, and the interior transitions into the de Sitter phase. That transition releases energy, some of which goes into forming the shell, and the rest radiates away. The object settles into equilibrium, and what you're left with is a compact sphere with no singularity, no event horizon, and a surface that sits just outside the radius where the horizon would have been. That surface, the outer edge of the shell, is often called the gravastar surface. It is not a hard boundary in the sense of a solid object. It is more like a phase boundary, the place where one kind of space-time geometry gives way to another. One way to think about it is to imagine freezing water. At 0 degrees Celsius, liquid water and solid ice can coexist. The boundary between them is sharp. On one side, molecules are flowing freely. On the other, they are locked into a crystal lattice. The transition happens at a specific temperature, and it releases energy in the form of latent heat. The gravastar shell is analogous. On one side, you have the de Sitter interior, a region where space-time is uniform and static. On the other, you have the Schwarzschild exterior, a region where space-time curves around a central mass. The boundary between them is the shell, and crossing that boundary means transitioning from one phase of space-time to another. The energy required to maintain that boundary comes from the extreme pressure in the shell, which in turn is balanced by the outward push from the de Sitter core. That balance is delicate. If the core pressure drops, the shell collapses inward and you get a black hole. If the shell weakens, the exterior geometry destabilizes. The gravastar, assuming it can form in the first place, exists in a narrow slice of parameter space, where everything has to be just right. That fragility is both a feature and a bug. It means gravastars, if they exist, are rare and specific objects, not a generic endpoint like black holes, but it also means they are testable. If you can measure the properties of a compact object precisely enough, you might be able to rule out the gravastar interpretation, or confirm it. The original Mazur-Mottola model was intentionally simple. They used a thin shell approximation, treated the interior as pure de Sitter space, and ignored complications like rotation, charge, or magnetic fields. Real astrophysical objects are messier. Stars rotate. They have magnetic fields. The collapse process is not perfectly symmetric. Later papers attempted to generalize the gravastar model to account for those complications, with mixed success. Adding rotation turns out to be particularly tricky. A rotating gravastar would have to maintain its shell structure while spinning, and the centrifugal forces add extra stress to an already stressed system. Some studies suggested the shell might fragment or destabilize under rotation. Others found parameter ranges where rotating gravastars could still be stable, but those ranges were narrow. Charge is less of an issue. Most astrophysical black holes are thought to be electrically neutral, because any net charge would be neutralized quickly by pulling in oppositely charged particles from the surrounding environment. If the same logic applies to gravastars, then charge can be ignored, but magnetic fields are harder to dismiss. Neutron stars, the immediate precursors to black holes or gravastars, have extraordinarily strong magnetic fields, in some cases reaching trillions of times the strength of Earth's field. What happens to that field during the collapse? Does it get trapped in the shell? Does it thread through the de Sitter core? Does it disrupt the phase transition? These are open questions, and the answers depend on details of the collapse process that we do not yet understand. One interesting feature of the gravastar model is that it makes the dark energy component of the universe, the mysterious force accelerating cosmic expansion, a local rather than purely cosmological phenomenon. In standard cosmology, dark energy is spread uniformly throughout space, producing a gentle repulsive effect that only becomes noticeable on scales of billions of light years. In a gravastar, that same effect is concentrated in a region smaller than a city block. The de Sitter core is, in a sense, a bubble of dark energy compressed to densities and pressures that make it behave more like a solid than a diffuse cosmological field. That is strange. Dark energy, in the cosmological context, is so weak that you never notice it in your daily life. The gravitational pull of the Earth, the Sun, even the Milky Way, overwhelms it completely. But inside a gravastar, dark energy dominates. It is strong enough to counteract the crushing weight of a collapsing star. How does that happen? The answer comes down to the vacuum state of space-time. In quantum field theory, even empty space is not truly empty. It is filled with fluctuating fields, virtual particles popping in and out of existence, and a baseline energy density called the vacuum energy. That energy density is positive and it acts like a repulsive force. In flat, uncurved space-time, the vacuum energy is so small that it is nearly impossible to measure directly. But in curved space-time, especially in regions where the curvature is extreme, the vacuum state can change. The fluctuations can become more intense, the energy density can increase, and the repulsive effect can grow strong enough to matter. Mazur and Mottola proposed that during the collapse of a massive star, the space-time curvature becomes so steep that the vacuum undergoes a phase transition, condensing into a state with much higher energy density. That condensed vacuum is what fills the gravastar core. This is where the name gravitational vacuum condensate star comes from. It is not a star in the traditional sense, a ball of fusing hydrogen held up by thermal pressure. It is a region of space-time where the vacuum itself has condensed into a new phase, a phase that generates enough pressure to halt the collapse. The mechanism is loosely analogous to Bose-Einstein condensation, the quantum phenomenon where a gas of atoms cooled to near absolute zero suddenly transitions into a state where all the atoms occupy the same quantum state. In that case, the transition is driven by temperature. In the gravastar case, the transition is driven by gravity. The collapsing star compresses space-time so intensely that the vacuum can no longer remain in its normal state. It has to change, and when it does, the result is a stable, non-singular object held up by its own quantum vacuum. That explanation raises as many questions as it answers. What triggers the phase transition? How fast does it happen? What determines the size and pressure of the resulting core? Mazur and Mottola did not provide detailed answers. Their model was a framework, not a complete theory. But the framework was enough to show that the idea was mathematically self-consistent. You could write down the equations, solve them, and get a stable configuration. The physics might be exotic, but it was not nonsense. That was enough to keep the proposal alive. The early response from the astrophysics community was skeptical but not hostile. Most physicists were willing to entertain the idea as an interesting theoretical exercise, but few were ready to take it seriously as a description of real objects. The problem was observational. As long as gravastars and black holes looked identical from the outside, there was no way to tell them apart. And without a way to test the model, it remained speculative, no matter how elegant the mathematics. That began to change with the advent of gravitational wave astronomy. The first detection, in September 2015, showed that we could measure the masses and spins of merging compact objects with astonishing precision. And as more detections followed, it became clear that gravitational waves carried information about the internal structure of the merging objects, information that might be subtle enough to distinguish between a black hole and a gravastar. The key difference would show up in the ring-down phase, the final moments after the merger when the newly formed object settles into its equilibrium shape. A black hole rings like a bell, emitting gravitational waves at specific frequencies determined by its mass and spin. A gravastar would also ring, but the frequencies would be slightly different because the interior structure is different. The de Sitter core and the tension shell would affect how the object vibrates. If you could measure those frequencies precisely enough, you could test whether the object has a horizon or a surface. So far, the data is not precise enough. The differences between the two scenarios are smaller than the noise in the detectors, but future detectors, like the Laser Interferometer Space Antenna scheduled to launch in the 2030s, will have the sensitivity to probe those details. That is when the gravastar hypothesis will face its first real test. In the meantime, the model has continued to evolve. Researchers have proposed variations that replace the thin shell with a continuous transition layer, making the structure more physically plausible. Others have explored whether the phase transition could be triggered by quantum effects near the collapsing core, providing a mechanism rather than just asserting that the transition happens. Some studies have even suggested that gravastars, if they exist, might be more common in the early universe where conditions were more extreme and phase transitions more likely. None of these variations have been confirmed, but they have kept the idea in circulation, ensuring that gravastars remain part of the conversation about alternatives to black holes. What makes the gravastar proposal intellectually compelling is not that it solves every problem. It does not. The model still requires exotic matter, extreme pressures, and a phase transition we have never observed. But it demonstrates something important. The singularity is not inevitable. General relativity does not force you to accept infinite density and infinite curvature as the final word. There are other solutions, other endpoints, other ways for a collapsing star to finish its journey. Whether nature takes advantage of those alternatives is an open question. But the fact that the alternatives exist, that they are mathematically consistent and observationally viable, changes the conversation. It forces physicists to ask not just what happens when a star collapses, but what could happen. And in a field where we are still groping toward a complete theory of quantum gravity, that distinction matters. The gravastar is a heresy, in the sense that it challenges the orthodoxy of black hole physics, but it is a carefully argued heresy built on the same mathematical foundation as the models it seeks to replace. It does not reject general relativity. It extends it, applying it in ways that most physicists had not seriously considered. And in doing so, it opens the door to a possibility that has profound implications for how we understand the universe. If gravastars are real, then the most extreme objects we observe, the compact remnants of dead stars, the supermassive monsters at the centres of galaxies, are not bottomless pits where information goes to die. They are phase boundaries, places where space-time itself transitions from one state to another, places where the vacuum condenses, where pressure becomes a force strong enough to stop a collapsing star, and where the rules change in ways we're only beginning to explore. That is the promise of the Gravastar model, and that promise, however speculative, is enough to keep physicists looking for ways to test it. Because if the Heresy is correct, then we have been misidentifying the universe's most extreme objects for decades, and the truth, as always, is stranger than the story we have been telling. The Gravastar model asks you to believe in something that sounds like it belongs in a science fiction novel. A collapsing star, moments away from forming a black hole, suddenly undergoes a phase transition, and its interior fills with something that pushes outward instead of falling inward. That something has a name in the physics literature: dark energy. And it is contained inside a thin shell held together by pressures so extreme that they make the core of a neutron star look like a vacuum chamber. We are talking about 10 to the power of 45 Pascals, a number so absurdly large that it stops having intuitive meaning the moment you write it down. But before we can understand what that pressure means and why it is necessary, we need to talk about what dark energy actually is. Because most people, when they hear that term, picture something mysterious and poorly understood. And they are right. Dark energy is mysterious, it is poorly understood, but it is also real, and it has been measured. In the late 1990s, 2 independent teams of astronomers were studying distant supernovae, trying to measure how fast the universe was expanding and whether that expansion was slowing down over time. Everyone expected it to be slowing. Gravity pulls everything together. The expansion of the universe, which began with the Big Bang, should be gradually losing steam as galaxies tug on each other across the void. That was the prediction. The observation said otherwise. The distant supernovae were dimmer than expected, which meant they were farther away than they should be if the expansion was slowing. The universe was not decelerating, it was accelerating. Something was pushing space itself apart, and that something was not gravity. It was the opposite of gravity, an outward pressure filling every cubic meter of empty space, too weak to notice on the scale of planets or galaxies, but strong enough to dominate the entire universe once you zoom out far enough. Astronomers called it dark energy, and in 2011 the leaders of those 2 teams were awarded the Nobel Prize in Physics for discovering it. We still do not know what dark energy is. The most popular explanation is that it is a property of space itself, a kind of baseline energy density that comes with a vacuum. Quantum field theory predicts that empty space should have a non-zero energy density because of fluctuations in the quantum fields that permeate the universe. Particles and antiparticles pop into existence for fractions of a second, borrow energy from the vacuum and then annihilate, paying the energy back. Those fluctuations are happening everywhere all the time, even in the darkest, emptiest regions of the cosmos. And the net effect of all that activity is a positive energy density. The vacuum weighs something, and when space has energy, it also has pressure. In this case, negative pressure. Positive energy density, negative pressure. That combination sounds contradictory, but it is exactly what you need to produce a repulsive gravitational effect. In general relativity, gravity is not just about mass. It is about energy and pressure. The full Einstein field equations, the ones that describe how matter and energy curve spacetime, include terms for pressure as well as density. Most of the time, pressure is negligible. The pressure inside a planet or a star is tiny compared to the mass. But dark energy is different. The pressure is negative, and in the equations, negative pressure acts like a repulsive force. It pushes space apart. That is what is driving the accelerated expansion of the universe. Space itself, filled with this negative pressure vacuum energy, is being pushed outward against the pull of all the matter trying to hold it together. And because the vacuum energy density stays roughly constant as the universe expands, while the density of matter gets diluted, dark energy eventually wins. That is the universe we live in today. Most of its energy content is dark energy, and it is pushing everything apart. Now take that same phenomenon and shrink it down. Instead of filling the entire universe, concentrate it in a region smaller than a city. Instead of a gentle outward push barely noticeable across billions of light years, crank up the energy density until the pressure becomes strong enough to halt the collapse of a star. That is what Mazur and Mottola proposed happens inside a gravastar. The core, instead of collapsing to infinite density, transitions into a state where the vacuum energy density jumps to an enormous value. The spacetime inside that region becomes de Sitter space, a geometry where the curvature is uniform and the dominant force is the negative pressure of the vacuum, and that pressure pushes out, balancing the inward pull of gravity and stopping the collapse before a singularity forms. The equation of state that describes this kind of matter is simple to write down. Pressure equals negative energy density. In symbols, you would write it as P equals negative rho. That is the defining property of dark energy. The pressure is exactly equal to the energy density but with a negative sign. Normal matter, the kind you are made of, has positive pressure and positive energy density. If you compress it, the pressure increases. Dark energy does the opposite. If you try to compress dark energy, the negative pressure increases, pushing back harder. It is self-stabilizing. The more you squeeze it, the more it resists. That property is what makes it useful for holding up a gravastar. But here is the problem. The cosmological dark energy we observe filling the universe has an energy density of about 10 to the negative 9 joules per cubic meter. That is unimaginably small. You could take a cube of empty space a kilometer on each side, and the total dark energy inside it would barely be enough to lift a grain of sand. That is the energy scale driving the accelerated expansion of the universe. It works on cosmological scales because the universe is enormous. But on the scale of a collapsing star, that energy density is useless. It would not even register. For dark energy to halt the collapse of a stellar core, the energy density would have to be something like 50 orders of magnitude larger. 10 to the power of 40 joules per cubic meter or more. That is not a small adjustment. That is a fundamental change in the state of the vacuum. And this is where the gravastar model veers into territory that makes even sympathetic physicists uncomfortable. There is no known mechanism that would cause the vacuum energy density to suddenly jump by 50 orders of magnitude during a stellar collapse. In cosmology, dark energy is a constant. It does not change. It does not respond to the presence of matter or to the curvature of space-time. It just sits there, the same everywhere, pushing gently on everything. Mazur and Motola proposed that in the extreme conditions near the endpoint of gravitational collapse, the vacuum undergoes a phase transition. The normal vacuum state, with its tiny cosmological energy density, becomes unstable, and the vacuum condenses into a new state with much higher energy density, a gravitational vacuum condensate. The analogy they invoked was Bose-Einstein condensation, the quantum phenomenon where a gas of atoms at near absolute zero suddenly transitions into a state where all the atoms drop into the same quantum ground state. That transition happens abruptly at a critical temperature, and it produces a macroscopic quantum object with properties that are radically different from the original gas. The gravastar core would be similar, a macroscopic region of space-time where the vacuum itself has condensed into a new phase. The energy density in that phase is not the cosmological value. It is much, much higher. High enough to produce negative pressures strong enough to counterbalance the gravitational pull of the entire collapsing star. The result is a stable configuration. The core pushes out. The surrounding matter pushes in. The forces balance, and the object settles into equilibrium without ever forming a singularity. That is the idea. Whether it actually happens is a completely different question, because phase transitions like the one being proposed here do not occur in any regime we have tested experimentally. We have never created conditions in a laboratory that come close to the densities and curvatures present in a collapsing stellar core. We have theoretical models, extrapolations based on quantum field theory and general relativity, but no direct observations. The gravastar hypothesis is asking us to trust that those extrapolations are correct, and that the vacuum really does behave this way under extreme conditions. Even if you accept that the core can transition into a high-density dark energy state, you still have to explain how the structure stays stable, and that brings us to the shell. The thin boundary layer separating the de Sitter interior from the Schwarzschild exterior. This is where the numbers get truly absurd. The shell in the simplest gravastar models is infinitesimally thin. Not thin in the sense of a few meters or even a few millimeters. Thin in the sense of approaching zero thickness. It is a mathematical surface, a boundary between two different space-time geometries, and it has to support an enormous amount of tension to keep those two geometries from collapsing into each other. The stress in that shell is where the 10 to the power of 45 Pascals figure comes from. And it is worth pausing to understand what that number actually means. A Pascal is a unit of pressure. 1 Pascal is 1 Newton per square metre, roughly the pressure exerted by a small apple resting on a table. Atmospheric pressure at sea level is about 100,000 pascals. The pressure at the bottom of the Mariana Trench, the deepest point in Earth's oceans, is about 100 million pascals. The pressure at the centre of the Earth, where the inner core is being squeezed by the weight of the entire planet, is around 360 gigapascals. 360 billion pascals. That is the most extreme pressure you can find anywhere on Earth. Now go to a neutron star. The pressure in the core of a neutron star, where atomic nuclei are crushed so tightly that protons and neutrons merge into a soup of quarks, is roughly 10 to the power of 34 pascals. That is 100 million trillion pascals, a number so large that it stops having any connection to everyday experience, and yet the Gravastar shell exceeds that by another 11 orders of magnitude. 10 to the power of 45 pascals, a billion times more extreme than the core of a neutron star. To put it another way, if you took a region the size of a sugar cube and subjected it to 10 to the power of 45 pascals of pressure, the force on each face of that cube would be equivalent to the weight of about 1 billion suns. That is the stress the Gravastar shell has to withstand. Not for a fraction of a second during some transient event, but continuously, for as long as the Gravastar exists. The shell is not made of atoms. It cannot be. No atomic lattice could survive that kind of stress. The forces would rip apart the electron clouds, crush the nuclei, and reduce the entire structure to a plasma of quarks and gluons within nanoseconds. The Gravastar shell, in the models that attempt to describe it, is something else. A surface layer with no rest mass but non-zero surface energy and surface pressure. It is more like a field configuration than a physical object, a kink in the space-time geometry where the interior and exterior solutions meet. The equation of state for the shell is usually written as pressure equals energy density. In symbols, P equals RO, that is the opposite of the core where pressure equals negative energy density. The shell is made of what physicists call stiff matter, or ultra-relativistic matter, a hypothetical substance where the pressure is as large as the energy density itself. No known form of matter behaves this way under normal conditions. Even in the core of a neutron star, the pressure is much smaller than the energy density. But in the Gravastar shell, the pressure has to be that large. Otherwise, the structure collapses. The shell is under tension, being pulled outward by the negative pressure of the dark energy core and pulled inward by the gravitational attraction of the mass outside. To keep those forces balanced, the tension in the shell has to be enormous, 10 to the power of 45 pascals enormous. And here is the part that should make you deeply uncomfortable. We have no idea what kind of physics would produce a shell like that. The equation of state, P equals ρ, can be written down. The solution to Einstein's equations can be constructed. The model is mathematically self-consistent. But that does not mean it corresponds to anything real. Physicists have a term for matter that behaves in ways we have never observed. Exotic matter. And the Gravastar shell is exotic in the most extreme sense of the word. It requires pressures and energy densities far outside anything we have tested, held together by mechanisms we do not understand, in a configuration that might not be stable once you account for quantum fluctuations or perturbations from the outside environment. The shell is a placeholder for physics we do not have yet. Some researchers have tried to make the shell more physically plausible by replacing the infinitely thin boundary with a continuous transition layer. Instead of a sharp jump from de Sitter geometry to Schwarzschild geometry, the transition happens gradually over a finite thickness. The pressure and energy density vary smoothly from the core to the exterior, and the shell becomes a region rather than a surface. That approach has the advantage of avoiding delta functions and other mathematical artifacts that make physicists nervous. But it does not solve the underlying problem. You still need extreme pressures. You still need exotic matter. You have just spread it out over a slightly larger volume. The numbers get a little less absurd, but they do not become comfortable. Another variation replaces the stiff matter shell with a layer of something called phantom energy, a hypothetical form of dark energy, with an equation of state where the pressure is even more negative than the energy density. Phantom energy, if it exists, would be even more exotic than ordinary dark energy. It would violate all the classical energy conditions that physicists use to ensure matter behaves in physically reasonable ways. Most cosmologists are skeptical that phantom energy is real, but it shows up in the theoretical literature because it solves certain problems in models of the universe's far future. In the gravastar context, phantom energy could provide the tension needed to stabilize the shell without requiring the infinitely thin boundary of the original model. But again, this is speculation layered on speculation. Phantom energy has never been observed. Its existence is purely hypothetical. Using it to explain how a gravastar holds together is like solving one mystery by invoking a bigger mystery. The core issue is that the gravastar model requires the vacuum to do things we have never seen the vacuum do. In everyday physics, the vacuum is passive. It is the background, the stage on which matter and fields interact. It does not push. It does not pull. It does not undergo phase transitions. But in quantum field theory, the vacuum is more active. It has structure. It can fluctuate. And under the right conditions, it can change state. The Higgs field, for example, is a quantum field that fills all of space, and the vacuum state of the Higgs field determines the masses of fundamental particles. In the early universe, when temperatures were extremely high, the Higgs field was in a different vacuum state, and particles had different masses than they do today. As the universe cooled, the Higgs field underwent a phase transition, settling into its current vacuum state. That transition was abrupt, and it had profound consequences for the physics of the universe. The gravastar hypothesis is proposing something analogous. During the collapse of a massive star, the conditions become so extreme that the vacuum undergoes a phase transition. The normal vacuum state becomes unstable, and the vacuum condenses into a new state with much higher energy density. That new state fills the core of the collapsing star, and its negative pressure halts the collapse. The analogy to the Higgs transition is suggestive, but it is not proof. The Higgs transition happened at temperatures around 1 trillion degrees, energies we can reproduce in particle accelerators. The gravastar transition, if it happens at all, would occur at energies and densities far beyond anything we can test. We are extrapolating from known physics into a regime where the extrapolation might break down, and we have no way to check. One way to think about the gravastar core is as a bubble of false vacuum. In cosmology, a false vacuum is a state where the energy density is higher than the true ground state, but the system is stuck there because transitioning to the lower energy state requires overcoming an energy barrier. False vacuums are unstable over long timescales. Eventually, quantum tunneling allows a small region to transition to the true vacuum, and that transition spreads outward at the speed of light, converting the false vacuum into true vacuum and releasing the energy difference. Some inflationary models of the early universe rely on false vacuum transitions to explain why the cosmos underwent a period of exponential expansion in the first fraction of a second after the Big Bang. The idea is that the universe started in a false vacuum state, inflated rapidly while it was stuck there, and then transitioned to the true vacuum, reheating the universe and producing all the particles and radiation we see today. If the gravastar core is a false vacuum, then it might be unstable on very long timescales. Quantum tunneling could eventually allow a small region of the core to transition back to the normal vacuum state. That transition would propagate outward, and the gravastar would collapse. Or it might explode. The details depend on how much energy is released during the transition, which depends on the energy density difference between the two vacuum states. If the energy release is large, the gravastar could detonate like a bomb, radiating energy across the surrounding spacetime. If the release is small, the collapse might be slower, more like a deflating balloon than an explosion. Either way, the gravastar would not be stable forever. It would have a finite lifetime set by the rate of quantum tunneling, and eventually it would cease to exist. That is a problem if you want gravastars to explain the long-lived compact objects we observe in the universe. Black holes, or things we have been calling black holes, have been around for billions of years. If gravastars are inherently unstable, they would have decayed long ago. Mazur and Mottola did not address this issue in their original paper, but later studies have explored whether the gravastar core could be stabilized against tunneling. One possibility is that the extreme curvature near the core suppresses the tunneling rate, making the decay timescale longer than the current age of the universe. Another is that the core is not a false vacuum at all, but a genuine ground state, a configuration where the high energy density is stable because it minimizes some effective potential that accounts for both quantum and gravitational effects. If that is the case, the gravastar would be stable indefinitely. But again, this is speculative. We do not have a detailed model of the potential that would produce this behavior. We are guessing. The pressure in the shell is so extreme that it raises questions about whether spacetime itself can handle it. General relativity is a classical theory. It treats spacetime as a smooth continuum that can be curved by matter and energy, but never torn or broken. At the scales where quantum effects become important, around the Planck length of 10 to the negative 35 meters, that assumption might fail. Spacetime might have structure. It might be discrete rather than continuous, more like a lattice of points than a smooth fabric. If that is true, then there is a limit to how much stress spacetime can support before the classical description breaks down. That limit is set by the Planck energy density, roughly 10 to the power of 113 joules per cubic meter. The Gravastar shell at 10 to the power of 45 Pascals corresponds to an energy density well below the Planck scale. So in principle, spacetime should be able to handle it, but we do not know for sure. We have never tested general relativity in regimes where the stress energy is that extreme. The theory might hold, or it might crack. One of the more unsettling aspects of the Gravastar shell is that it is not just under pressure, it is under tension. Tension means the shell is being stretched like a rubber band pulled tight. But the shell has no thickness, it is a surface, so what exactly is being stretched? The answer, as far as the mathematics is concerned, is the geometry itself. The shell is a boundary where spacetime transitions from one curvature to another, and maintaining that transition requires the geometry to support a non-zero surface stress. Think of it like the surface of a soap bubble. The bubble is held together by surface tension, the tendency of the liquid film to minimize its area. The film itself is thin, but the tension is real. You can measure it by how much force is required to stretch the bubble. The Gravastar shell is similar, except instead of a liquid film you have spacetime, and instead of minimizing area, you are balancing the curvature on either side of the boundary. The tension is encoded in the Einstein equations as a surface stress energy tensor, a mathematical object that describes how energy and momentum are distributed across the shell. The fact that the shell is a surface rather than a volume has bothered some physicists. Surfaces in general relativity are usually treated as idealized boundaries, useful for calculations but not meant to represent real physical objects. The Gravastar model takes that idealization seriously and asks us to believe that the surface is not just a mathematical convenience, but an actual feature of the object. That is a hard sell. Real objects have volume, they have interiors. A surface with no thickness feels more like a cartoon than a physical structure. Later Gravastar models, as mentioned earlier, tried to fix this by giving the shell a finite thickness. But doing so introduces new complications. If the shell has volume, then you need to specify an equation of state for the matter filling that volume, and you need to ensure that matter can support the required stress. Most equations of state that describe known forms of matter cannot do that. The pressures are too high, the matter would collapse or explode, so you are back to exotic matter, just spread over a larger region. There is also the question of what happens at the outer edge of the shell, where the Gravastar meets the surrounding spacetime. In the simplest models, the exterior is pure Schwarzschild geometry, the same spacetime you get around a non-rotating black hole. That means the Gravastar from the outside looks almost identical to a black hole. Same mass, same gravitational field, same light bending. The only difference is at the surface. A black hole has an event horizon, a boundary where light cannot escape. A Gravastar does not. The surface of a Gravastar sits just outside where the event horizon would be, close enough that light escaping from the surface is extremely redshifted, but far enough that it can still escape. That means a Gravastar is not completely black. It would emit light faintly from its surface. The light would be redshifted to very long wavelengths, deep in the infrared or even radio, depending on how close the surface is to the would-be horizon. Detecting that light would be extraordinarily difficult, but in principle, it is there. That emission is one of the few observational differences between a Gravastar and a black hole. If you could measure the spectrum of light coming from a compact object, and show that it is coming from a surface rather than an accretion disk or some other external source, you could distinguish between the two. The problem is that most compact objects are surrounded by material, gas, dust, accretion disks, jets. All of that material emits light, and it completely drowns out any faint emission from the object's surface. To see the surface directly, you would need a compact object that is completely isolated, with no surrounding matter, and you would need a telescope sensitive enough to detect extremely redshifted thermal radiation from something the size of a city. We do not have that capability yet, but future instruments, particularly space-based infrared telescopes, might. The gravastar shell also affects how the object responds to external perturbations. If you drop matter onto a gravastar, it does not fall through an event horizon and disappear. It hits the shell, and when it hits, it deposits energy and momentum. The shell has to absorb that impact, and the object's structure has to adjust to accommodate the additional mass. That adjustment would produce a transient signal, a burst of gravitational waves or electromagnetic radiation as the gravastar settles back into equilibrium. Black holes do something similar when they accrete matter, but the details are different. A black hole absorbs the infalling matter smoothly, with no hard surface to hit. A gravastar has a surface, and that surface responds to impacts in ways that could, in principle, be measured. Again, the differences are subtle, but they are there. One of the reasons the gravastar model has persisted in the literature, despite its many problems, is that it offers a way out of the singularity. Singularities are where physics breaks. They are places where the equations give up and tell you they cannot describe what is happening. Every physicist knows this is a red flag. When your theory predicts its own failure, it means the theory is incomplete. There is more to the story. The gravastar hypothesis is one attempt to finish that story without waiting for a complete theory of quantum gravity. It says the singularity is not inevitable. The collapse can be halted by a phase transition, and the endpoint is a stable object with no infinity problem and no breakdown of the equations. That is appealing. It is also, as we have seen, built on assumptions that have never been tested and mechanisms that have never been observed. But it is mathematically consistent, and in a field where we are still groping for the right answers, mathematical consistency is worth something. The exotic heart of the gravastar, the dark energy core and the ultra-stressed shell, is the feature that makes the model both fascinating and hard to accept. It is fascinating because it shows that general relativity, the same theory that predicts black holes, also allows for radically different endpoints to collapse. It is hard to accept because it requires us to believe in physics we have never seen. Dark energy condensates, stiff matter shells, phase transitions at densities we cannot reproduce. Pressures that exceed anything in the observable universe by orders of magnitude. Every one of those ingredients is speculative, and when you stack speculations on top of each other, the edifice becomes fragile. One wrong assumption, and the whole thing collapses. Not literally, though that might happen too, but intellectually. The model stops being a viable alternative and becomes just another exotic idea that sounded good on paper, but did not survive contact with reality. And yet the gravastar refuses to go away. It keeps reappearing in the literature, in new forms with new variations, as physicists try to refine the model and make it more realistic. That persistence suggests something interesting is happening here. Maybe not gravastars exactly as Mazur and Mottola described them, but something in that direction. Some way for collapsing stars to avoid the singularity, to transition into a stable configuration that looks like a black hole from the outside but is fundamentally different on the inside. If that possibility is real, then the pressures we have been discussing, the 10 to the power of 45 pascals holding the shell together, are not just abstract numbers. They are the signature of a new kind of object, a new state of matter, a new phase of space-time that only appears under the most extreme conditions the universe allows. And understanding what happens in that regime is not optional. It is necessary. Because if we cannot explain what happens at the endpoint of collapse, then we do not fully understand gravity. And a universe where we do not fully understand gravity is a universe full of surprises. Some of them, as we're about to see, are more disturbing than the black holes we thought we knew. We have been talking about exotic matter, impossible pressures, and phase transitions that may or may not happen during stellar collapse. All of that is strange enough. But now we need to confront the truly unsettling part of the gravastar hypothesis. The part that makes physicists pause and stare at the equations with something approaching dread. Because if gravastars are real, if these objects actually exist in the universe, they are not just alternatives to black holes. They are worse, far worse, in ways that have nothing to do with singularities or information paradoxes, and everything to do with what happens when you get too close. The difference comes down to two words: event horizon. A black hole has one, a gravastar does not. And that absence, that single missing feature, changes everything about how these objects interact with the universe around them. To understand why, you need to understand what an event horizon actually does. Most people, when they picture a black hole, imagine a boundary you cross and then you are trapped. That is correct, but it misses something crucial. The event horizon is not a wall. It is not a surface. It is not made of anything. It is a mathematical boundary in space-time, the place where the escape velocity equals the speed of light. Cross that boundary moving inward and you cannot turn around. Not because something is holding you, but because every path through space-time that leads away from the singularity also leads backward in time, and you cannot move backward in time, so you fall, inexorably, until you reach the centre. But here is the strange part. Crossing the event horizon itself does not hurt. If the black hole is large enough, supermassive, the kind that sits at the centre of a galaxy, the tidal forces at the horizon are negligible. You could cross it and not feel a thing. Your watch would still tick. Your heart would still beat. The stars behind you would redshift into oblivion, and the singularity ahead would loom closer with every passing moment, but the crossing itself would be smooth, gentle even. You would not know you had crossed until you tried to escape and realized every direction you could move led deeper inward. The tidal forces, the spaghettification, the part where your body gets stretched like taffy because your feet are being pulled harder than your head, that comes later. Closer to the singularity, at the horizon of a supermassive black hole, you are safe. Doomed, yes. Trapped, absolutely, but not yet torn apart. This is what physicists mean when they say the event horizon is, in a sense, safe. It is not a physical barrier. It does not crush you. It does not rip you apart. It is just a point of no return. And if the black hole is massive enough, you can cross it without even noticing. That is one of the more counterintuitive features of general relativity. The thing that traps you is not violent. It is geometry. Space-time itself has been bent so steeply that all future paths lead inward. The violence comes later, deep inside, where the tidal forces grow without bound as you approach the singularity. But the boundary itself, the horizon, is quiet. Now consider a gravastar. No event horizon, no singularity, just a surface. A thin shell of exotic matter under pressures we can barely conceptualize, sitting at almost exactly the radius where a black hole's event horizon would have been. That surface is physical. It is real. And when you approach it, you do not pass through into some hidden interior where the rules change. You hit it, or more precisely, the gravitational field of the gravastar, unshielded by any horizon, reaches out and begins tearing you apart long before you ever reach the surface. Because the surface is not a point of no return. It is a boundary with a gravitational pull so intense that the tidal forces near it make the interior of a black hole look forgiving. Let's unpack that. Tidal forces are the difference in gravitational pull across an object. If your feet are closer to a massive body than your head, your feet feel a stronger pull. The difference might be tiny if the body's far away or not very massive. But if the body is compact and heavy, the difference becomes significant. Your feet accelerate faster than your head, and your body stretches. The closer you get, the worse it gets. Near a black hole, tidal forces grow as you approach the singularity. But at the event horizon of a supermassive black hole, the tidal forces are weak. The radius is large, the curvature is gentle, and you can cross without being stretched. A gravastar has no singularity to hide the source of its gravity. The entire mass of the object is concentrated in or near the thin shell, and that shell sits at a radius only slightly larger than where the event horizon would have been. The compactness is almost the same, the gravitational field is almost the same, but there is no horizon to cross, there is only the approach. And as you get closer, the tidal forces do not wait until you reach some hidden interior. They start immediately, and they escalate without mercy. The surface gravity of a gravastar can be essentially as strong as that of a black hole. That phrase, essentially as strong, is doing a lot of work. What it means is that the acceleration due to gravity at the surface of a gravastar can approach the same value you would measure at the event horizon of a black hole with the same mass. For a solar mass black hole, the surface gravity at the horizon is about 1.5 times 10 to the power of 12 meters per second squared. That is about 150 billion times Earth's surface gravity. For a supermassive black hole weighing 1 billion solar masses, the surface gravity is much weaker, only a few times Earth gravity, because the horizon radius is proportionally larger. But in both cases, the tidal forces grow steeply as you get closer. A gravastar with the same mass as a solar mass black hole would have a surface gravity in the same range. 1.5 times 10 to the 12 meters per second squared. But here is the critical difference, that gravity is not hidden behind a horizon. It is right there, at the surface, pulling on anything that comes near. And the tidal forces, the stretching, the spaghettification, begin far outside the radius where a black hole's horizon would have been. Because the gravastar's surface is not a geometric boundary where you stop being able to escape. It is a physical object with a gravitational field that reaches outward, unimpeded, pulling harder and harder as you approach. Imagine you're falling toward a gravastar. You start far away, where the gravity feels weak. As you get closer, you begin to feel the pull. Stronger, faster, your velocity increases. But so does the tidal force. The difference in gravitational pull between your head and your feet starts to become noticeable. If you are falling feet first, your feet are accelerating faster than your head. You feel a stretching sensation, mild at first, then stronger, then unbearable, and you're still millions of kilometers from the surface. Far enough that if this were a black hole, you would not even be close to the horizon yet. But this is not a black hole. This is an object with no horizon, and the tidal forces are already tearing you apart. The numbers are brutal. For a solar mass gravastar, tidal force is strong enough to kill a human. Stretching the body beyond what flesh and bone can tolerate would begin at a distance of several hundred kilometers from the surface. For comparison, the event horizon of a solar mass black hole has a radius of about 3 kilometers. You could fall to within a few kilometers of a black hole and still be outside the horizon. At a gravastar, you would be dead long before you reach that distance, ripped apart by tides that grow without limit as you approach the shell. And if you somehow survived, if your body were made of something stronger than human tissue, you would eventually reach the surface. And the surface would not let you pass. This is where the gravastar model diverges most sharply from the black hole picture. A black hole has no surface. The event horizon is not a barrier you collide with. It is a region of space-time you pass through. Once you cross it, you keep falling until you hit the singularity. A gravastar has a surface, a real, physical boundary, and when you reach it, you do not pass through. You stop, or more accurately, you collide. The shell, that thin layer of exotic matter under unimaginable tension, does not absorb you. It reflects you, or it crushes you. The details depend on the model, but the outcome is the same. You do not fall through, you hit something. Some descriptions of gravastars refer to the shell as a reflecting surface. The idea is that matter or energy approaching the gravastar does not get absorbed into the interior, the way it would fall through a black hole's horizon. Instead, it encounters a boundary that pushes back. The shell, under all that tension, behaves more like a trampoline than a trapdoor. When something hits it, the shell deforms slightly, absorbs the impact and then rebounds, sending the object back outward. Or it simply crushes the object against the surface, compressing it into a thin smear of particles that then radiate away as energy. Either way, the gravastar does not swallow what falls onto it. It interacts with it, violently. That interaction is another feature that distinguishes gravastars from black holes. Black holes are information sinks, at least in the classical picture. Everything that crosses the horizon is lost to the outside universe. The black hole's mass increases, but the details of what fell in are erased. The gravastar does not do that. The surface is where the interaction happens and the details matter. If you drop a book onto a gravastar, the book does not disappear behind a horizon. It hits the shell. The energy of the impact gets redistributed. The shell vibrates, radiating gravitational waves. The book's matter gets compressed, heated, and likely converted into radiation. That radiation escapes. The information in the book, encoded in the quantum states of its atoms, is not lost. It is scrambled, yes, thermalized certainly, but not gone. The gravastar processes the book and spits out the pieces. And here is where things get genuinely terrifying. Because the shell is so close to where the event horizon would have been, The gravitational field just outside the shell is almost as extreme as the field just outside a black hole's horizon. Light emitted from the surface is enormously redshifted. Time dilation is severe. An observer far away watching something fall onto the gravastar would see the falling object slow down as it approaches the surface, just as they would with a black hole. The light from the object would redshift, dimming and shifting toward longer wavelengths. And as the object hits the surface, the observer would see a final burst of radiation, stretched and redshifted, as the impact energy gets radiated away. From a distance, the process looks almost identical to what happens when something falls into a black hole. The object appears to freeze at the boundary, dimming into invisibility. But the physics at the boundary is completely different. A black hole horizon is empty space. Curved, yes. Extreme, absolutely. But empty. A gravastar surface is not empty. It is a physical structure under pressures that defy comprehension. And anything that reaches it experiences forces that a black hole horizon simply does not exert. The tidal compression across the shell, as recent studies have noted, is intense. Matter falling onto the surface does not pass through smoothly. It gets compressed, sheared and torn apart by the structure of the shell itself. The shell is thin, but it is not passive. It pushes back. And the forces it exerts on anything trying to cross it are enough to disintegrate almost any form of matter. Think about what that means for anything orbiting close to a gravastar. A stable orbit near a black hole is possible, even close to the event horizon. The innermost stable circular orbit around a non-rotating black hole is at 3 times the Schwarzschild radius, about 9 kilometers for a solar mass black hole. Inside that radius, orbits become unstable, and anything there will spiral inward and cross the horizon. But outside that radius, you can orbit safely. The tidal forces are present but manageable, especially for a small object. A gravastar changes the calculation. The surface is a physical boundary, and orbits that would be stable around a black hole become dangerous near a gravastar because the tidal forces are stronger. The shell itself, with its extreme surface gravity, distorts the space-time around it in ways that make close orbits unstable or lethal. An object in a close orbit around a gravastar would experience tidal forces strong enough to stretch and compress it rhythmically as it moves through regions of varying gravitational intensity. Over time, those oscillating forces would heat the object, like squeezing a rubber ball repeatedly until it warms up. The heating would be intense, enough to melt rock, vaporize metal, and ionize any atmosphere the object might have. Eventually, the object would disintegrate, breaking apart into a cloud of hot gas that would either fall onto the gravastar or get flung outward by the violence of its own disruption. This process, called tidal disruption, happens near black holes too. But near a gravastar it happens at larger distances because the tidal forces extend farther from the surface. The danger zone is bigger, and then there is the surface itself. What would it look like? That question is harder to answer than it sounds because the answer depends on the model. In the simplest gravastar models, the shell is infinitesimally thin, a mathematical surface with no interior structure. You cannot ask what it looks like any more than you can ask what the event horizon of a black hole looks like. It is a boundary, not an object. But in more realistic models, where the shell has a finite thickness, the surface becomes something you could, in principle, describe. It would not be solid in any conventional sense. The matter making up the shell is not atomic. It is some kind of ultra-relativistic fluid or field configuration, a state of matter that exists only under the most extreme conditions. The surface would not have texture the way a planet's surface does. No mountains, no valleys, no features, just a perfectly smooth boundary, glowing faintly with thermal radiation, redshifted to the point of near invisibility. That glow is another difference from black holes. Black holes are black by definition. They emit Hawking radiation, but that radiation is extraordinarily faint and comes from quantum effects near the horizon, not from the horizon itself. A gravastar surface, by contrast, has a temperature. The shell is under tension, and that tension generates heat. The surface would radiate like any hot object, emitting light according to its temperature. But because the surface sits so close to where the event horizon would be, the light escaping from it would be enormously redshifted. What might be emitted as visible light or ultraviolet from the surface would arrive at a distant observer as infrared or even radio waves. The gravastar would not be completely black. It would be dim, faint, glowing in wavelengths that are hard to detect but technically present. Detecting that glow is one of the few ways to distinguish a gravastar from a black hole observationally. If you could isolate a compact object with no surrounding matter, no accretion disk, no jets, and measure its spectrum carefully, you might see the faint thermal emission from the surface. A black hole in the same situation would emit only Hawking radiation, which for any astrophysical black hole is far too faint to detect with current instruments. The gravastar surface emission, while also faint, would be stronger, not by much, but potentially enough to measure with next-generation infrared telescopes. That is a big if. Most compact objects we observe are surrounded by material, and that material outshines any surface emission by many orders of magnitude. But the possibility is there. The absence of an event horizon has another profound implication. It means the gravastar does not hide anything. A black hole once formed seals off its interior from the rest of the universe. Everything behind the horizon is causally disconnected. You cannot see it. You cannot measure it. You cannot interact with it. The horizon is a one-way boundary. Information can go in, but it cannot come out, at least not in any straightforward way. That is the essence of the information paradox. A gravastar has no such barrier. The surface is the boundary, and the boundary is part of the exterior universe. You can, in principle, measure it. You can probe it. You can send light toward it and watch how the light behaves when it reflects or scatters off the surface. The interior, the dark energy core, is hidden behind the shell, yes, but it is not causally disconnected. The shell interacts with the outside universe. It responds to perturbations, it radiates, it exists in the same space-time as everything else. That openness, paradoxically, makes gravastars more dangerous. A black hole traps its violence behind the horizon. The singularity, the place where space-time curvature becomes infinite and tidal forces diverge, is hidden. You cannot reach it without crossing the horizon, and once you cross, you are already doomed. The horizon acts as a shield, protecting the outside universe from the singularity. A gravastar has no such shield. The surface, with its extreme gravity and intense tidal forces, is right there, in contact with the outside universe. The violence is not hidden. It is present, immediate, and waiting for anything that comes too close. The term pure terror in the context of gravastars refers to this feature, not the singularity which gravastars avoid, not the event horizon which they lack, but the surface. The physical, tangible boundary where gravitational forces strong enough to rip apart stars are concentrated and exposed. A black hole kills you eventually, deep inside, where no one can see. A gravastar kills you on the way in full view of the universe, stretched and compressed by tidal forces that escalate without the mercy of a horizon to cross first. It is the difference between falling into a pit and hitting a wall. Both are deadly, but one hides the violence, the other displays it, and the wall, in this case, is not even stable in the conventional sense. The shell is under tension, held together by pressures that border on the physically impossible. If the shell were ever to fail, if the exotic matter holding it together were to destabilize or fragment, the gravastar would not simply collapse into a black hole, it might explode. The dark energy core, suddenly released from the confining tension of the shell, would expand violently. The energy stored in the shell and the core would be released in a burst that could rival a supernova. Or the collapse might proceed inward, the shell buckling under the gravitational load, and the object might transition into a black hole after all, swallowing the core and the shell together and forming an event horizon in the process. Either outcome would be catastrophic for anything nearby, and both are possibilities the gravastar model has to contend with. Some studies have explored the stability of gravastar shells under perturbations. What happens if you drop a large mass onto a gravastar? Does the shell absorb the impact and settle back into equilibrium, or does the added mass push the structure past some critical point, causing it to collapse? The answer depends on the details of the shell's equation of state and the strength of the dark energy core. In some parameter ranges, the gravastar is stable. It can absorb small perturbations and return to equilibrium. In other ranges, the structure is fragile. A sufficiently large perturbation could trigger a collapse or an explosion. The boundary between stability and instability is sharp, and we do not know where real gravastars, if they exist, sit relative to that boundary. There is also the question of what happens when two gravastars collide. We have detected gravitational waves from dozens of black hole mergers. The signals match the predictions of general relativity with extraordinary precision. If some of those events involved gravastars instead of black holes, the signals would be slightly different. The differences would show up in the ring-down phase, the final moments after the merger when the newly formed object settles into equilibrium. A black hole rings at specific frequencies determined by its mass and spin, frequencies that have been calculated and measured. A gravastar would ring at different frequencies because its internal structure is different. The shell and the dark energy core would affect how the object vibrates. Those frequency differences are small, but they are calculable, and with sensitive enough detectors, they might be measurable. The challenge is that the differences are buried in noise. Current gravitational wave detectors like LIGO and Virgo can measure the masses and spins of merging objects, but they cannot yet resolve the fine details of the ring-down waveform well enough to distinguish between a black hole and a gravastar. Future detectors, particularly space-based observatories like LISA, will have better sensitivity in the frequency range where those differences matter. If gravastars are real, and if they merge with each other or with black holes, LISA should be able to see the signature. That is one of the most concrete observational tests on the horizon. But even if we detect a gravastar, even if the ring-down waveform shows unambiguous evidence of a shell and a dark energy core, the terror remains. Because the physics of the surface does not go away. A gravastar, confirmed or not, is an object with gravitational forces strong enough to tear apart anything that approaches. The tidal forces near the surface are not a theoretical curiosity. They are a direct consequence of the object's compactness and the absence of an event horizon, and they make gravastars in a very real sense more dangerous than the black holes they replace. A black hole hides its violence behind a boundary. A gravastar puts it on display. There is something deeply unsettling about that. We have spent decades getting comfortable with the idea of black holes. They are extreme, yes, mysterious certainly, but also, in a strange way, safe. The event horizon protects us from the singularity. Whatever horrors lie inside, they are sealed off from the rest of the universe. We can study black holes from a distance, measure their properties, and never have to confront the singularity directly. It is out of reach, hidden behind a boundary we cannot cross without sacrificing any hope of return. The gravastar model strips away that protection. It says the boundary is not a horizon, it is a surface. And that surface is every bit as extreme as the singularity it replaces, with the added terror that it is accessible. You can reach it, you can interact with it, and it will destroy you long before you ever get close. That is the cosmic paradox. No singularity, so the equations do not break. No event horizon, so information is not lost. But in exchange, you get an object whose surface gravity and tidal forces make it a more immediate, more visceral threat than any black hole. The gravastar solves the theoretical problems that have plagued black hole physics for decades, and in doing so, it creates a new kind of danger. Not hidden, not abstract, but right there, at the boundary between the object and the universe, waiting. The terror is not in what the gravastar hides, it is in what it exposes, a region of space-time where gravity is so strong, so unrelenting, that approaching it means certain death. Not at some distant singularity, unreachable and theoretical, but at the surface, meters away, or kilometers, or however close you can get before the tides pull you apart, and every meter closer makes it worse. If black holes are the universe's locked doors, places where space-time itself forbids entry and seals off the interior, then gravastars are the universe's exposed blades, sharp, unshielded and lethal to anything that comes within reach. The difference matters. And as we move forward, as we compare these two kinds of objects in detail, that difference is going to become impossible to ignore. Because the question is no longer just whether gravastars exist. The question is what it means if they do. What it means to live in a universe where the most compact objects are not bottomless pits, but physical structures, held together by forces we barely understand, radiating violence from their surfaces without the courtesy of a horizon to hide behind. That is the paradox, and that is the terror. No singularity to break the equations, no horizon to trap the light, just a surface, infinitesimally thin, unimaginably stressed, and gravitationally stronger than anything else in the cosmos, waiting. We have spent the last 3 chapters building a picture of the gravastar, a collapsing star that undergoes a phase transition instead of forming a singularity, a core filled with dark energy pushing outward, a shell under pressures so extreme they make neutron star cores look gentle, and a surface that sits just outside where a black hole's event horizon would be, unshielded, violent, and ready to tear apart anything that approaches. That is the Gravastar. An object that solves some of the deepest problems in theoretical physics, while introducing a new kind of danger we never had to worry about with black holes. But now we need to stop and ask the obvious question: how do you tell the difference? If you are an astronomer sitting at a telescope, looking at a compact object millions or billions of light years away, how do you know whether you're looking at a black hole or a gravastar? Both have enormous mass. Both bend light. Both produce gravitational waves when they merge. Both would appear as dark, compact objects surrounded by glowing accretion disks if they are feeding on nearby matter. From a distance, they look almost identical. So identical that some researchers have concluded there is no observational way to distinguish between them with current technology. That statement, blunt and unsettling, appears in the literature analysing gravitational wave events, and it raises a troubling possibility. What if we have been cataloguing gravastars for years, calling them black holes, and never noticed the difference? The comparison starts with the interior. A black hole, in the standard picture, has two defining features: an event horizon and a singularity. The horizon is the boundary where escape velocity equals the speed of light. Cross it and you cannot get out. The singularity is the endpoint of collapse, the place where all the infalling matter piles up and the density becomes infinite. That is the model. Simple, elegant, and built on general relativity. The problem is the singularity. Infinite density means the equations break. The theory cannot describe what happens there. It is a placeholder for physics we do not understand. And sitting behind that placeholder is the information paradox, the unresolved contradiction between general relativity, which says information is lost when it crosses the horizon, and quantum mechanics, which says information can never be destroyed. A gravastar replaces both features with something different. No event horizon, no singularity. Instead, the interior is a region of de Sitter space, a geometry where the vacuum energy density is high, and the pressure is negative. That negative pressure pushes outward, counterbalancing the inward pull of gravity. The collapse halts before a singularity forms, and the object settles into a stable configuration. The core is uniform, static, and completely free of the infinities that plague black hole models. Surrounding the core is the shell, a thin boundary layer under enormous tension. The shell is where the geometry transitions from the de Sitter interior to the Schwarzschild exterior. It is made of exotic matter, a state we have never observed, held together by pressures in the range of 10 to the power of 45 Pascals. And outside the shell, far from the object, the spacetime looks exactly like the spacetime around a black hole. Same mass, same curvature, same gravitational field. That last detail is why distinguishing between the two is so hard. If you measure the gravitational field from a safe distance, you get the same answer whether the object is a black hole or a gravastar. Gravity does not care what is inside. It only cares about the total mass and how it is distributed. A spherical object with a given mass produces a specific gravitational field, and that field extends outward, bending light, curving space-time, pulling on nearby matter in exactly the way general relativity predicts. Black holes and gravastars, as long as they have the same mass, produce the same field. You cannot tell them apart by looking at how light bends around them or how stars orbit nearby. The external geometry is identical, but the differences are there, buried in details that only show up under specific conditions. The first difference is the boundary. A black hole has an event horizon, a one-way membrane where light and matter can cross inward but never escape. A gravastar has a surface, a physical boundary where the shell meets the outside universe. That surface is not a horizon. Light can escape from it, barely. The surface sits just outside where the horizon would be, so close that the gravitational redshift is enormous, but not infinite. Photons climbing out of the gravitational well lose most of their energy, shifting from visible light or ultraviolet into the infrared or even radio. The gravastar is not black. It is dim, faint, glowing in wavelengths that are hard to detect, but it glows. Detecting that glow is easier said than done, Most compact objects we observe are not isolated. They sit in the centres of galaxies surrounded by gas and dust. Or they are part of binary systems pulling matter off a companion star. That matter forms an accretion disk, a swirling ring of hot plasma that emits enormous amounts of light across the entire electromagnetic spectrum. The light from the accretion disk drowns out any faint thermal emission from the surface. To see the surface directly, you would need a compact object that is completely isolated, with no surrounding material, and you would need a telescope sensitive enough to detect extremely redshifted light from something the size of a city sitting millions of light years away. We do not have that capability yet. But future instruments, space-based infrared telescopes with enormous collecting areas and exquisite sensitivity, might. The second difference is how the objects respond to infalling matter. When something falls into a black hole, it crosses the event horizon and disappears from the outside universe. The black hole's mass increases slightly, but the details of what fell in are erased. The black hole has no hair, as the saying goes. It does not remember whether it swallowed a star, a gas cloud, or a spaceship. All that matters is the total mass, charge, and spin. A gravastar behaves differently. Matter falling onto a gravastar does not cross a horizon. It hits the surface. The impact deposits energy and momentum into the shell. The shell vibrates, adjusting its structure to accommodate the new mass. And the vibrations radiate outward as gravitational waves. That radiation is detectable, in principle. When a gravastar absorbs matter, it rings like a bell, emitting gravitational waves at specific frequencies determined by the object's mass, the properties of the shell, and the equation of state of the dark energy core. Those frequencies are different from the frequencies a black hole would emit in the same situation. The differences are small, a few percent at most, but they are calculable. If you could measure the gravitational wave signal from an object accreting matter with enough precision, you could distinguish between a black hole and a gravastar. The problem again is sensitivity. Current gravitational wave detectors are not precise enough to resolve those differences, but the next generation of detectors will be. The third difference shows up during mergers. When two black holes collide, they spiral inward, emit gravitational waves, and eventually merge into a single black hole. The process has three phases. The inspiral, where the two objects orbit each other and gradually lose energy to gravitational waves. The merger, where the horizons touch and the objects combine. And the ringdown, where the newly formed black hole settles into equilibrium, vibrating at specific frequencies as it sheds excess energy. Those ringdown frequencies are called quasi-normal modes, and they depend only on the mass and spin of the final black hole. General relativity predicts them with extraordinary precision, and every gravitational wave detection we have made so far matches those predictions. A gravastar merger would look similar. Two gravastars spiraling inward, emitting gravitational waves, merging into a single object. The inspiral phase would be almost identical to a black hole inspiral because the external gravitational fields are the same. But the merger and ringdown would be different. When two black holes merge, their event horizons combine smoothly, and the resulting object is a larger black hole with a well-defined horizon and singularity. When two gravastars merge, their shells collide. The impact is violent. The shells compress, heat up, and release energy. The dark energy cores might merge or they might destabilize, triggering a phase transition that converts the gravastar into a black hole or causes it to explode. The details depend on the properties of the shell and the core, but the outcome is not guaranteed to be a stable gravastar. It could be a black hole, it could be a burst of radiation, it could be something else entirely. If the merger does produce a stable gravastar, the ringdown phase would be different from a black hole ringdown. The quasi-normal modes would depend not just on the mass and spin of the final object, but also on the internal structure. The shell, the core, the transition layer between them. All of those features affect how the object vibrates. The frequencies would be shifted slightly compared to a black hole, and the damping rates, how quickly the vibrations die away, would also be different. Those shifts are small, but they are there, and with sensitive enough detectors, they are measurable. Several studies have calculated the expected quasi-normal modes for gravastars and compared them to black hole predictions. The results vary depending on the model, but the general conclusion is that gravastars can, in principle, be distinguished from black holes through gravitational wave observations. The key is the ringdown phase. That is where the internal structure matters most. A black hole rings in a way that is completely determined by its mass and spin. A gravastar rings in a way that also depends on the shell and the core. The difference is subtle, but it is real, and it is one of the few clean observational signatures that could confirm or rule out the gravastar hypothesis. The Laser Interferometer Space Antenna, LISA, is a space-based gravitational wave observatory scheduled to launch in the 2030s. It will be sensitive to lower frequency gravitational waves than LIGO and Virgo, the ground-based detectors that have been operating since 2015. LISA will observe supermassive black hole mergers, or what we have been calling supermassive black hole mergers, at the centers of distant galaxies. Those events are rare, but when they happen, they produce gravitational wave signals that last for hours or even days. LISA will be able to measure those signals with exquisite precision, resolving features in the waveform that are completely inaccessible to ground-based detectors. If supermassive gravastars exist and if they merge, LISA should see the difference in the ringdown. That is the test. That is when we will know. But even if LISA detects a gravastar, even if the ringdown frequencies match the predictions and the shell signature is unmistakable, the comparison with black holes does not end there. Because the gravastar model makes specific predictions about other phenomena, predictions that differ from the black hole picture in ways that might already be observable. One of those predictions concerns the information paradox. The black hole information paradox is one of the most famous unsolved problems in theoretical physics. It goes like this. In quantum mechanics, information is never destroyed. If you know the exact state of a system at one moment, you can predict its state at any future moment and reconstruct its state at any past moment. That property is called unitarity, and it is a cornerstone of quantum theory. But black holes seem to violate it. When matter falls into a black hole, it crosses the event horizon and is lost to the outside universe. The black hole's mass increases, but the details of what fell in are erased. The black hole does not remember. Then, over enormous timescales, the black hole evaporates via Hawking radiation, a quantum process that slowly saps the black hole's mass. When the black hole finally evaporates completely, the information that fell in is gone. Destroyed. Unitarity violated. Physicists have been arguing about this for 50 years. Some claim the information is encoded in the Hawking radiation, smuggled out in correlations too subtle to detect. Others propose the information is stored at the event horizon, holographically imprinted on the surface. A few suggest the paradox is telling us that black holes do not have true event horizons, that something prevents the horizon from forming in the first place. That last idea, the no-horizon hypothesis, is where gravastars fit in. A gravastar has no event horizon. The surface is a physical boundary, not a one-way membrane. Information that falls onto a gravastar does not cross a horizon and disappear. It hits the shell. The shell absorbs the impact, heats up, and radiates the energy away. The information, encoded in the quantum states of the infalling matter, is scrambled and thermalized, yes, but not lost. It is converted into radiation that escapes. The gravastar processes the information and spits it out. Unitarity is preserved. The paradox evaporates. That sounds like a neat solution, but it is not without problems. The information that comes out is scrambled beyond recognition. If you drop a book onto a gravastar, the book's atoms get compressed, heated and converted into a burst of thermal radiation. That radiation carries the information technically, but in a form that is completely inaccessible. You would need to measure the quantum state of every photon in the burst, and then run a calculation that is, for all practical purposes, impossible. The information is preserved in principle but lost in practice. Whether that counts as solving the information paradox depends on how strict you want to be about the definition of information recovery. Some researchers argue that practical recovery is not the point. The point is that unitarity is not violated. The quantum evolution is reversible, even if the reversal is too complicated to carry out. Others are less satisfied. They point out that black holes, if they evaporate via Hawking radiation, also preserve unitarity in principle. The information might be encoded in the radiation, even if we cannot extract it. The gravastar does not necessarily solve anything that black hole models with modified horizons or quantum corrections could not also solve. It just does so without invoking an event horizon. Whether that is an advantage or just a different way of stating the same problem is a matter of debate. But there is another angle to the information story, one that makes gravastars more appealing. Black holes, in the classical picture, are one-way streets. Everything that crosses the horizon is trapped forever. That trapping is what creates the information problem in the first place. Gravastars do not trap anything. The surface reflects or absorbs, but it does not hide. That openness means gravastars do not suffer from the same causal disconnect that makes black holes so mysterious. The interior of a gravastar, the dark energy core, is behind the shell, yes, but it is not behind a horizon. It is part of the same space-time as the exterior. In principle, you could probe it. You could send signals toward the surface and watch how they scatter or absorb. The gravastar is not sealed off from the universe. It interacts. That interaction is another feature that distinguishes gravastars from black holes. Black holes are passive. They sit in space, bending light, pulling on nearby matter, but they do not actively push back. The event horizon is not a barrier that exerts force. It is a geometric boundary, a region where the curvature is so steep that all future paths lead inward. Gravastars are active. The shell is under tension, held together by forces that push outward against the gravitational pull. When something hits the shell responds. It vibrates, it heats, it radiates. The gravastar is not a pit you fall into, it is a structure you collide with. And that difference, subtle as it sounds, changes the dynamics of how these objects interact with their surroundings. Consider accretion, the process where matter falls onto a compact object and forms a disk. Black holes accrete matter all the time. Gas from a companion star or from the surrounding interstellar medium spirals inward, forms a hot disk, and eventually crosses the event horizon. The disk glows brightly as the gas heats up from friction and gravitational compression, emitting X-rays and other high-energy radiation. But the black hole itself does not contribute to the light. It is black. The event horizon absorbs everything that crosses it. All the light we see comes from the disk, not the hole. A gravastar accretes differently. The matter still forms a disk, still heats up, still emits radiation. But when the matter reaches the surface, it does not disappear. It hits the shell. The impact releases energy, heating the surface. The surface glows, not brightly, because the light is enormously redshifted, but it glows nonetheless. That surface emission, faint as it is, adds to the total luminosity of the system. The gravastar plus disk combination might be slightly brighter than a black hole plus disk with the same mass and accretion rate. The difference would be small, a few % at most, but it would be there, and in principle it is measurable. If you could isolate the surface emission from the disk emission, if you could model the disk precisely enough to subtract its contribution and see what is left, you might detect the surface glow. That has not been done yet. But it is a possibility. There is also the question of what happens to the matter that hits the surface. Does it stick? Does it get absorbed into the shell, increasing the gravastar's mass? Or does it bounce off, reflected by the extreme tension in the shell? The answer depends on the model. In some gravastar scenarios, the shell is so rigid that matter cannot penetrate it. The surface acts like a trampoline, absorbing the impact and rebounding. The infalling matter gets compressed, heats up, and is flung back outward as a burst of radiation. The gravastar does not grow. It just processes the matter and spits it out. In other scenarios, the shell is more flexible. It can absorb matter, incorporate it into the boundary layer, and grow thicker over time. The gravastar accretes slowly, like a black hole, but the matter never crosses a horizon. It gets trapped in the shell, adding to the object's mass without ever reaching the core. Both scenarios have observational consequences. A reflecting surface would produce bursts of radiation every time a significant amount of matter hits it. An absorbing surface would grow steadily, and the shell thickness would increase. Neither behavior matches the simple picture of a black hole swallowing everything that crosses the horizon. If we could observe the accretion process in enough detail, we might be able to distinguish between the two. The problem, once again, is that the details are buried in noise. The accretion disk is bright, the surface is dim. Separating the two requires precision we do not yet have. Then there is Hawking radiation. One of the strangest predictions of black hole physics is that black holes are not perfectly black. They emit radiation, faint thermal glow that comes from quantum effects near the event horizon. The mechanism is subtle. Virtual particle-antiparticle pairs pop into existence near the horizon. Normally they annihilate almost immediately, But if one member of the pair falls into the black hole and the other escapes, the escaping particle becomes real, carrying energy away from the black hole. Over time, the black hole loses mass. It evaporates. The process is extraordinarily slow. A solar mass black hole would take 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. But for smaller black holes, primordial black holes that might have formed in the early universe, the evaporation timescale is shorter, and the radiation, faint as it is a real prediction of quantum field theory in curved space-time. Gravastars do not have event horizons, so do they emit Hawking radiation? The answer is complicated. In the simplest gravastar models, where the object is static and stable, there is no Hawking radiation. The surface is not a horizon, and the quantum process that generates Hawking radiation relies on the horizon geometry. Without a horizon, the process does not happen. The gravastar just sits there, cold and dark, not evaporating. But more recent models, ones that account for the formation process and the dynamics of the shell, suggest something different. During the collapse, as the star transitions into a gravastar, the geometry near the surface becomes highly curved and dynamic. Quantum effects in that regime can produce thermal radiation similar to Hawking radiation. The temperature of that radiation is tied to the Gibbons-Hawking temperature of the de Sitter core, a quantum effect associated with the cosmological horizon inside the gravastar. The result is that gravastars might emit thermal radiation after all, not from an event horizon, but from the surface and the core. If that prediction is correct, then gravastars and black holes both radiate, but for different reasons. Black holes radiate because of the horizon, gravastars radiate because of the core. The spectra might be similar, but the underlying physics is different, and in principle, you could distinguish between the two by measuring the radiation carefully. The problem, predictably, is that the radiation is too faint to detect for any astrophysical object. Hawking radiation from a stellar mass black hole is undetectable with current or foreseeable instruments. The same is true for gravastar surface emission. We can predict it, model it, calculate it, but we cannot measure it. Not yet. The comparison between gravastars and black holes also extends to the enigmatic phenomena we have been attributing to black holes for decades. High-energy jets, gamma-ray bursts, the intense radiation from active galactic nuclei. All of these are powered, we think, by black holes. The standard model is that matter falling into a black hole releases enormous amounts of gravitational energy. Some of that energy gets funneled into jets, narrow beams of plasma and radiation that shoot outward at nearly the speed of light. The jets are launched by magnetic fields threading through the accretion disk, twisted and amplified by the rotation of the black hole. It is a well-developed picture, supported by simulations and observations. Gravastars could produce the same phenomena. The accretion disk around a gravastar would behave almost identically to the disk around a black hole. Same magnetic fields, same rotation, same energy release. The jets would launch in the same way. From a distance, you would not be able to tell the difference, but close to the surface, the dynamics might change. The shell, with its extreme surface gravity and physical boundary, could affect how the magnetic fields thread through the inner disk. The impact of matter hitting the surface could generate shock waves that propagate outward, heating the disk and amplifying the radiation. The gravastar might be slightly more efficient at producing jets, or slightly less, depending on how the shell interacts with the infalling matter. The differences would be subtle, but they would be there. And if we could measure the jet properties precisely enough, if we could resolve the inner disk structure and see how the flow behaves near the surface, we might be able to distinguish between a black hole and a gravastar. One intriguing possibility is that some of the most extreme high-energy events we observe, ultra-luminous X-ray sources, fast radio bursts, certain classes of gamma-ray bursts, could be powered by gravastars rather than black holes. The gravastar surface, with its reflecting boundary and intense tidal forces, might produce bursts of radiation that black holes cannot. When matter hits the shell, the energy release could be sudden and violent, producing a brief, intense flash. If the gravastar is rotating, the surface might develop hotspots, regions where the shell is thicker or the tension is higher. Those hotspots would emit more radiation, and as the gravastar rotates, the radiation would sweep across the sky like a lighthouse beam. We would see periodic flashes, bursts that repeat on timescales of milliseconds or seconds. Some fast radio bursts have exactly that pattern, periodic, repeating, with brightness variations that suggest a rotating source. Could they be gravastars? It is speculative, but it is not impossible. Another area where gravastars might differ is in their long-term stability. Black holes once formed are stable indefinitely. They do not decay, except via Hawking radiation, and that process takes longer than the age of the universe for any astrophysical black hole. Gravastars, by contrast, are held together by a delicate balance of forces. The dark energy core pushes out, the shell pushes in. If that balance is disturbed, the structure could collapse or explode. Quantum tunneling could allow the core to transition back to the normal vacuum state, triggering a catastrophic event, or the shell could fragment, destabilize, and fall inward, converting the gravastar into a black hole. The timescale for these processes is unknown. It could be longer than the age of the universe, in which case gravastars are effectively stable. Or it could be shorter, in which case gravastars are transient objects that eventually decay. If gravastars are unstable, then the number of gravastars in the universe would decrease over time. Old gravastars would collapse or explode, and new ones would form from collapsing stars. The population would reach a steady state where the formation rate equals the decay rate. That steady state could be measured in principle by counting compact objects and looking for trends in their properties. If gravastars are common, we might see a population of young, unstable objects mixed with older, more stable ones. If gravastars are rare or if they decay quickly, we might not see them at all. The data so far does not show any clear trend. But we have only been detecting gravitational waves for a decade. The sample size is still small. There is one more comparison worth making, and it is perhaps the most important. Black holes, as they are currently understood, are incomplete. The singularity is a placeholder for physics we do not have. The information paradox is unresolved. The connection between general relativity and quantum mechanics is missing. Black holes are a success story of classical physics, but they are also a signpost pointing toward the limits of that success. They tell us we need something more. Gravastars, if they are real, offer one path toward that something more. They replace the singularity with a phase transition, a quantum effect that happens at densities we have never tested, but that is consistent with the principles of quantum field theory. They eliminate the event horizon, removing the boundary that creates the information paradox. They provide a concrete model, built on general relativity and quantum mechanics, that avoids the infinities and the contradictions. That is not a guarantee that gravastars are correct, but it is a demonstration that alternatives exist, that the singularity is not inevitable, that the universe might have found a way around the problems we thought were inescapable. The cosmic showdown between gravastars and black holes is not just a contest between two theoretical models, it is a test of how we understand the universe at its most extreme. Black holes have been the reigning champions for more than half a century. They fit the data, they explain the observations, they have survived every test we have thrown at them. But they come with unresolved problems, deep cracks in the foundation that we have been papering over with promises of future theories. Gravastars are the challengers. They offer solutions to those problems, but they come with their own baggage. Exotic matter, extreme pressures, phase transitions we have never seen. The question is not which model is simpler, it is which model is true, and the only way to answer that is to look, to measure, to probe the universe with instruments sensitive enough to see the differences, the ring-down frequencies in gravitational waves, the faint thermal glow from the surface, the way matter behaves when it hits the boundary. The signatures are there, waiting. And in the next decade, as new detectors come online and new observations are made, we will finally have the tools to test the models. The showdown is not over, it is just beginning. And the outcome, whatever it turns out to be, will reshape our understanding of gravity, space-time, and the fate of collapsing stars. If black holes win, we keep the singularity and the information paradox, and we wait for quantum gravity to save us. If gravastars win, we get a universe without singularities, without horizons, and without the safety of a boundary that hides the violence inside. We get a universe where the most extreme objects are not bottomless pits but physical structures, exposed and dangerous, held together by forces that push the limits of what space-time can handle. Either way, the universe is stranger than the story we have been telling, and the truth, as always, is waiting in the data. So you want to know if gravastars are real? That is the question hanging over everything we have discussed so far. The theory is elegant. The mathematics works. The model solves problems that have haunted black hole physics for decades. But none of that matters if gravastars do not actually exist in the universe. And the frustrating, uncomfortable truth is that after more than 2 decades of searching, we still do not have direct proof. We have observations of compact objects, thousands of them. We have detected gravitational waves from mergers. We have imaged the shadows of supermassive black holes. We have catalogued X-ray binaries, gamma-ray bursts, active galactic nuclei, all powered by something extremely massive and extremely small, and every single one of those observations is consistent with black holes. But here is the problem. Every single one of those observations is also consistent with gravastars. The two models produce almost identical signatures from a distance. Same mass, same gravitational field, same light bending. The differences are there, buried in subtle details that require precision we do not yet have, and instruments we have not yet built. Distinguishing a gravastar from a black hole is not impossible, but it is hard, extraordinarily hard. And the quest for proof, the search for observational evidence that would confirm gravastars exist or rule them out definitively, is one of the most challenging experimental programs in modern astrophysics. This is that story, the search for something we cannot see directly, hidden inside objects that already defy intuition, using techniques that push the limits of what our telescopes and detectors can measure. The most promising avenue for detecting gravastars comes from gravitational waves. When two compact objects merge, black holes or gravastars or anything in between, they emit gravitational waves that ripple outward through space-time at the speed of light. Those waves carry information about the masses, spins, and internal structure of the merging objects. And if you can measure the waveform precisely enough, you can decode that information. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravitational wave signal in September 2015. It came from the merger of two black holes, each weighing about 30 solar masses, colliding more than 1 billion light-years away. The signal matched the predictions of general relativity so precisely that it left no room for doubt. We were seeing space-time itself vibrate, carrying the imprint of two massive objects spiraling together and combining into one. Since then, LIGO and its European counterpart Virgo have detected more than 90 gravitational wave events. Most of them are black hole mergers, a few are neutron star mergers, and every single waveform so far fits the black hole model. No deviations, no anomalies, no smoking gun evidence for anything exotic. But absence of evidence is not evidence of absence. The reason we have not seen gravastar signatures yet is not necessarily because gravastars do not exist. It is because the signatures are subtle, and our detectors are only just reaching the sensitivity required to see them. The key difference between a black hole merger and a gravastar merger shows up in the ring-down phase, the final moments after the two objects combine when the newly formed object settles into equilibrium. A black hole rings like a struck bell, emitting gravitational waves at specific frequencies called quasi-normal modes. Those frequencies depend only on the mass and spin of the final black hole, nothing else. General relativity predicts them with extraordinary precision, and every ring-down we have measured matches those predictions. A gravastar would ring differently because its internal structure is different. The shell, the dark energy core, the boundary between the two, all of those features affect how the object vibrates. The quasi-normal mode frequencies would be shifted slightly compared to a black hole. And the damping rates, how quickly the vibrations die away, would also be different. The shifts are small, a few % at most, but they are calculable and they are measurable, in principle. The problem is noise. Gravitational wave detectors are exquisitely sensitive, but they are not perfect. The signals we detect are buried in background noise from seismic vibrations, thermal fluctuations, and quantum uncertainty in the detector mirrors. The ring-down phase is the faintest part of the waveform. It comes after the inspiral and the merger, when the signal amplitude has already dropped significantly. By the time the object is ringing, the signal-to-noise ratio is low, and extracting the quasi-normal mode frequencies with enough precision to distinguish between a black hole and a gravastar requires data quality we do not quite have yet. LIGO and Virgo are sensitive, but they are not sensitive enough to resolve the fine details of the ring-down for most events. The differences between the two models are smaller than the noise, but there is another signature, and it is potentially much clearer: echoes. If a gravastar has a physical surface instead of an event horizon, gravitational waves produced during the merger do not just radiate outward into space. Some of them bounce off the surface, reflect back inward, and then scatter outward again after a delay. The result is a series of repeating pulses, echoes of the original merger signal, arriving at the detector at regular intervals after the main event. The time delay between echoes depends on the size of the object and the location of the surface. For a gravastar with a surface just outside where the event horizon would be, the delay is short, milliseconds or less. But it is there, and it is detectable if you know what to look for and if the signal is strong enough. Searches for gravitational wave echoes began almost immediately after the first LIGO detections. Researchers took the publicly available data from the black hole mergers, analysed it with algorithms designed to pick out faint repeating signals, and looked for evidence of echoes. Some studies reported hints. Weak signals buried in the noise that could be interpreted as echoes if you squinted hard enough. Others found nothing. The statistical significance of the claimed detections was low, and the broader community remained skeptical. The problem, once again, was noise. The echoes, if they exist, are faint, fainter than the ring-down. And extracting them from the background requires careful modelling, precise templates, and high signal-to-noise ratios, none of which we have in abundance yet. The quest for gravitational wave echoes is ongoing. Every new detection adds to the dataset, and every improvement in detector sensitivity brings us closer to the threshold where echoes, if they are there, will become unambiguous. The next generation of gravitational wave observatories will make a decisive difference. LIGO is currently being upgraded to a configuration called a Plus, which will improve sensitivity by about a factor of 2. That might be enough to see echoes, if gravastars are common, and if the echo amplitude is on the higher end of the predicted range. Beyond that, there are plans for detectors like Cosmic Explorer in the United States and Einstein Telescope in Europe. Both are ground-based observatories with arms several times longer than LIGO's, and both will have sensitivity 10 times better or more. With those instruments, gravitational wave echoes from gravastar mergers, if they happen, will be unmissable. And then there is LISA. The Laser Interferometer Space Antenna is a space-based gravitational wave observatory, scheduled to launch in the 2030s. It will consist of 3 spacecraft flying in a triangular formation, separated by millions of kilometers, using laser beams to measure the distance between them with nanometer precision. LISA will detect gravitational waves at much lower frequencies than LIGO, in the millihertz range rather than tens to hundreds of hertz. That frequency range is where supermassive black holes or supermassive gravastars merge. Those events are rare, but when they happen, they produce signals that last for hours or days. LISA will measure those signals in exquisite detail, resolving features in the waveform that are completely inaccessible to ground-based detectors. If supermassive gravastars exist and if they merge, LISA will see the difference in the ring-down. The quasi-normal modes, the echoes, the subtle shifts that distinguish a surface from a horizon, that is the test. That is when we will know for sure whether the universe contains objects more exotic than black holes. But gravitational waves are not the only way to search for gravastars. There is also light, electromagnetic radiation, the glowing accretion disks, the jets, the X-rays and gamma rays that pour out of compact objects feeding on nearby matter. Most compact objects we observe are not isolated. They sit in binary systems pulling gas off a companion star. That gas spirals inward, forming a hot disk that emits enormous amounts of radiation. The disk is where the action is, and the disk, it turns out, is sensitive to whether the object at the centre has an event horizon or a surface. The difference comes down to something called the hard surface effect. A black hole has no surface. Matter falling through the event horizon crosses smoothly, disappearing from the outside universe without any final burst of energy. The innermost stable circular orbit around a black hole, the point where orbits become unstable and matter plunges inward, sits at about 3 times the Schwarzschild radius. Inside that radius, the disk effectively ends. The matter spirals inward and vanishes. The energy it radiates comes from friction and gravitational compression in the disk, not from the crossing itself. A gravastar has a surface. Matter does not disappear. It hits, and when it hits, The energy of the impact gets released. The surface heats up. The collision produces shock waves, radiation, a final burst of energy that a black hole does not have. That burst changes the disk's spectrum. For a black hole, the temperature of the innermost part of the disk is set by the energy being radiated as the gas spirals inward. For a gravastar, the temperature is higher because of the additional energy from surface impacts. The disk around a gravastar should be slightly hotter, slightly brighter, with a spectrum that peaks at higher energies. The difference is small, a few percent, but it is there. And if you could measure the disk spectrum precisely enough, if you could model the emission from the innermost regions with enough accuracy, you might be able to distinguish between a black hole and a gravastar. Several studies have calculated what the disk spectra should look like for gravastars with different shell properties and compared them to black hole models. The predictions vary depending on the details, but the general conclusion is that gravastars produce hotter, harder spectra. More X-rays, fewer soft photons. The effect is strongest for rapidly rotating objects and for disks that extend all the way down to the surface. The problem is that accretion disk models are messy. Real disks are turbulent, magnetic, and three-dimensional. They have coronae, outflows, winds, jets. All of those features complicate the spectrum, and measuring the emission from the innermost regions, the parts closest to the compact object, requires high-resolution spectroscopy and timing analysis. Current X-ray observatories like NuSTAR and XMM Newton have the sensitivity to detect differences in disk spectra, but the differences are comparable to the uncertainties in the models. We can measure the spectra, we can fit them with models, but we cannot yet say definitively whether the data favours a surface or a horizon. The models are not precise enough, the data is not clean enough. Future X-ray missions will help. The Athena X-ray Observatory, scheduled to launch in the early 2030s, will have spectral resolution and sensitivity far beyond anything currently flying. It will measure disk spectra with enough precision to constrain the innermost stable circular orbit and test whether the disk extends all the way to a surface. That is a direct test of the hard surface effect. If gravastars are common, Athena should see the signature: higher temperatures, harder spectra, evidence of surface impacts. If gravastars are rare or do not exist, the spectra will match the black hole predictions, and the hard surface effect will remain a theoretical curiosity. There is also the question of jets. Many compact objects launch jets, narrow beams of plasma and radiation that shoot outward at nearly the speed of light. The jets are powered by magnetic fields threading through the accretion disk and anchored in the compact object's spin. For black holes, the Blandford-Zanayak mechanism is the leading explanation. Magnetic field lines thread through the event horizon, extracting rotational energy from the black hole and channeling it into the jet. The process is efficient, converting up to 40% of the infalling mass energy into jet power. A gravastar does not have an event horizon. The magnetic field lines cannot thread through a horizon that does not exist. Instead, they thread through the surface, the shell. And the shell, with its extreme tension and physical boundary, interacts with the magnetic field in ways that a horizon does not. The shell can anchor the field more strongly, or it can disrupt it depending on the shell's properties. The result is that gravastar jets might be more powerful or less powerful than black hole jets, or they might have different structures, different opening angles, different variability patterns. The details are model dependent, and simulations of gravastar jets are still in their infancy, but the possibility is there. If gravastars produce jets that are observationally distinct from black hole jets, we could identify them through jet properties alone. One intriguing possibility is that some of the most extreme high-energy events we observe could be powered by gravastars. Ultraluminous X-ray sources, for example, are compact objects that emit X-rays at luminosities far above what a stellar mass black hole should be able to produce. The leading explanation is that they are intermediate mass black holes, weighing hundreds or thousands of solar masses, accreting at high rates. But another possibility is that they are stellar mass gravastars with hard surfaces. The surface impacts and the enhanced disk emission could boost the luminosity, making a stellar mass gravastar look like a more massive black hole. The same logic applies to fast radio bursts, mysterious millisecond duration pulses of radio emission that arrive from distant galaxies. Some fast radio bursts repeat, with periodic or quasi-periodic timing that suggests a rotating source. A rotating gravastar with hotspots on the surface where the shell is under more tension or where matter is piling up could produce exactly that kind of signal. The surface glows. The gravastar rotates. The glow sweeps across the sky like a lighthouse. We see a burst every time the hotspot points toward us. It is speculative, but it is testable. If fast radio bursts come from gravastars, the burst properties, the spectra, the polarization, should match the predictions of surface emission rather than magnetar flares or other conventional models. Observations are ongoing, and the data is piling up. So far, no smoking gun. But the search continues. Another detection channel involves pulsar timing arrays. Pulsars are neutron stars that spin rapidly and emit beams of radio waves from their magnetic poles. As the neutron star rotates, the beam sweeps across the sky, and if the beam points toward Earth, we see a pulse of radio emission. The pulses are extraordinarily regular, ticking away with the precision of atomic clocks. Some pulses, called millisecond pulses, are even more stable, spinning hundreds of times per second with timing variations measured in nanoseconds over decades. Those pulses can be used as detectors for gravitational waves. The idea is simple. A gravitational wave passing between Earth and a pulsar stretches and compresses the space in between, changing the distance the radio pulses have to travel. That change shows up as a tiny shift in the arrival time of the pulses. By monitoring dozens of pulsars scattered across the sky and looking for correlated timing shifts, astronomers can detect gravitational waves at much lower frequencies than LIGO. Nanohertz frequencies, waves with periods of months to years, the kinds of waves produced by supermassive black hole binaries orbiting each other at the centers of distant galaxies. Pulsar timing arrays have been operating for more than a decade, and in 2023, 4 major collaborations announced evidence for a nanohertz gravitational wave background. Not a single source, but a stochastic hum of gravitational waves coming from all directions, the combined signal of thousands or millions of supermassive black hole binaries across the universe. The evidence ranged from weak to compelling depending on the dataset, but all 4 teams saw the same general pattern. Timing variations correlated across pulsars, consistent with a gravitational wave background. The detection was a milestone, proof that pulsar timing arrays work and that we can use them to probe the low-frequency gravitational wave universe. And it opened the door to a new question. Are those signals coming from black holes, or could some of them be coming from gravastars? The answer depends on whether gravastars produce different gravitational wave signals than black holes in the nanohertz regime. For supermassive binaries, the inspiral phase is slow. The objects orbit each other for thousands or millions of years before they merge. During that time, they emit gravitational waves continuously, and those waves propagate across the universe, building up a background. If one or both objects in the binary is a gravastar instead of a black hole, the inspiral waveform would be almost identical. The external gravitational fields are the same. The differences would only show up close to the merger, when the objects start to interact more strongly. At that point, the surface of the gravastar would matter. The tidal distortion, the energy lost to surface vibrations, the way the shell responds to the gravitational pull of the companion. All of those effects would alter the waveform slightly. And if pulsar timing arrays can measure the waveforms from individual binaries, rather than just the background, they might be able to detect those alterations. That capability is coming. The next generation of pulsar timing arrays, with more pulsars, longer baselines, and better timing precision, will be able to resolve individual supermassive binaries. The first detections are expected within the next decade, and once we start measuring those signals, we can compare them to the predictions for black holes and gravastars. If the waveforms match the black hole model, gravastars are ruled out or at least constrained. If the waveforms show deviations, if there are echoes or frequency shifts or anomalies that do not fit the black hole picture, then we have evidence for something exotic. Gravastars, or objects like them. The pulsar timing array data is accumulating, the sensitivity is improving, and the tests are coming. There is also the possibility of indirect evidence, unusual stellar orbits, strange dynamics in galactic cores, compact objects that behave in ways black holes should not. One example is the supermassive object at the center of our own galaxy, Sagittarius A star. It weighs about 4 million solar masses, and it sits at the exact center of the Milky Way, surrounded by a cluster of stars orbiting at velocities that exceed 10,000 kilometers per second. Those stars, particularly a handful of bright ones designated S stars, have been tracked for decades with telescopes in Chile and Hawaii. Their orbits trace out ellipses around Sagittarius, a star, and by measuring those orbits with exquisite precision, astronomers have tested general relativity in the strong field regime. So far, every test has confirmed Einstein's predictions. The orbits behave exactly as general relativity says they should. No deviations, no anomalies. But if Sagittarius A star were a gravastar instead of a black hole, would the orbits be different? The answer is probably not. The external gravitational field of a gravastar is essentially identical to that of a black hole with the same mass. The orbits of distant stars would not change, but closer in, within a few gravitational radii, the differences might show up. A gravastar surface, with its extreme tidal forces and physical boundary, could affect how matter and light behave near the object. Stars passing very close to the surface, within a few Schwarzschild radii, might experience tidal forces stronger than expected for a black hole, or they might see their light bent in slightly different ways as it grazes the surface. Those effects would be tiny, but they might be measurable with next-generation instruments like the Extremely Large Telescope or space-based infrared observatories. The key is to catch a star on a very close passage and measure its trajectory and light curve with extreme precision. If the data shows deviations from the black hole predictions, gravastars become a viable explanation. If the data matches the predictions perfectly, gravastars are constrained. Another indirect test involves gravitational lensing. Light from a distant star or galaxy passing near a compact object gets bent by the object's gravity, and the amount of bending depends on the mass and the geometry. A black hole produces a specific lensing pattern, with light rays bending around the event horizon and forming a ring called the photon sphere. The shadow of a black hole, the dark region in the center of the image, corresponds to the event horizon plus the photon sphere. The Event Horizon Telescope, the global network of radio dishes that imaged the supermassive black hole in Messier 87, measured that shadow with unprecedented precision. The size and shape matched the black hole predictions almost perfectly, but a gravastar would produce a slightly different shadow. The surface sits outside where the event horizon would be, and the light bending near the surface is affected by the shell structure. Some models predict the gravastar shadow would be larger, some predict it would be smaller, depending on the shell thickness and the equation of state. The differences are subtle, but they are calculable. And if the Event Horizon Telescope or future Very Long Baseline interferometry networks can measure shadows with enough precision, they can test whether the observed objects have horizons or surfaces. Microlensing is another avenue. When a compact object passes in front of a background star, the gravitational field of the compact object magnifies the star's light. The magnification pattern depends on the mass and the size of the lensing object. A black hole produces a specific pattern, a brief brightening as the alignment improves, followed by a dimming as the alignment breaks. A gravastar might produce a slightly different pattern because of the surface. Light grazing the surface could scatter or reflect in ways that a horizon does not allow, adding small features to the magnification curve. Those features would be faint, but they would be there. And with large-scale microlensing surveys like those conducted by the Optical Gravitational Lensing Experiment or future space missions, we might be able to catch a gravastar in the act of lensing a background star. The statistics are daunting. Microlensing events are rare, and the odds of catching one where the lensing object is a gravastar and the light curve shows anomalies are slim. But with enough events, with enough data, the signal might emerge from the noise. The central challenge in all of these detection efforts is the same. Gravastars were designed, either intentionally or as a consequence of the physics, to mimic black holes as closely as possible. The external gravitational fields are identical. The light bending is almost identical. The accretion disk spectra are similar. The gravitational wave signals during the inspiral are indistinguishable. The differences only show up in fine details, the ring-down frequencies, the echoes, the hard surface effect, the subtle shifts in shadows and orbits, and those details are at or beyond the limits of what our current instruments can measure. We are not searching for something obvious, a glaring signature that jumps out of the data and announces itself. We are searching for whispers. Tiny deviations from the black hole model, buried in noise, requiring painstaking analysis and high precision to extract. It is the kind of search that takes decades, not years, and it requires patience, persistence, and instruments that have not been built yet. The technological hurdles are real. Gravitational wave detectors need to improve their sensitivity by at least an order of magnitude to see echoes clearly. X-ray observatories need better spectral resolution to constrain the hard surface effect. Pulsar timing arrays need more pulsars, longer baselines, and better timing models to isolate individual binary signals. Very long baseline interferometry networks need higher resolution and better sensitivity to measure shadows with the precision required to distinguish between horizons and surfaces. None of these improvements are impossible, but all of them are expensive, time-consuming, and require international collaboration on a scale that is hard to sustain. The quest for proof is not a sprint, it is a marathon, and we are only a few kilometers in. There is also the question of what counts as proof. Even if we detect a gravitational wave echo, even if the spectrum of an accretion disk shows evidence of a hard surface, even if a pulsar timing array sees an anomaly in a supermassive binary waveform, how do we know we are looking at a gravastar and not something else? Exotic compact objects are not limited to gravastars. There are dozens of other proposals in the literature. Boson stars, which are held together by scalar fields rather than nuclear forces. Fuzzballs, which are string theory objects with no horizon and no singularity. Planck stars, which are ultra-dense remnants where quantum gravity effects prevent collapse to a singularity. Quasi-black holes, which have horizons that form but never quite stabilize. Each of these alternatives has its own signatures, its own predictions, its own parameter space, and many of them overlap with the gravastar predictions. Distinguishing between them will require not just detecting a deviation from the black hole model, but measuring that deviation precisely enough to rule out the alternatives. That is a tall order, but the stakes are high. If gravastars are real, if we can confirm their existence through observation, then the entire story of stellar collapse changes. Black holes are no longer the only endpoint. Singularities are not inevitable. Event horizons are not guaranteed. The universe has found a way around the problems that have plagued theoretical physics for more than half a century. And the implications ripple outward, touching everything from quantum gravity to cosmology. If gravastars are not real, if the searches come up empty, and the observations continue to match the black hole model perfectly, then we know something different, but equally important. We know that nature does not take advantage of the loophole. The phase transition does not happen. The dark energy core does not form. The shell does not stabilize. And the singularity, with all its problems, is the true endpoint. Either way, the answer matters, and the only way to get the answer is to look, to measure, to push the instruments to their limits and see what the universe tells us. The quest for proof is ongoing. Gravitational wave detectors are being upgraded, X-ray observatories are being planned, pulsar timing arrays are adding more pulsars to their datasets. Very long baseline interferometry networks are improving their resolution, and every year the sensitivity improves, the data accumulates, and the tests get sharper. We are closer now than we have ever been to answering the question: do gravastars exist? Are they common? Are they rare? Are they the rule or the exception? The observations are coming. The technology is advancing, and within the next decade, possibly within the next few years, we will have data precise enough to test the models and see whether the universe has been hiding gravastars in plain sight all along. The signatures are subtle, the challenges are real, but the tools are being built. And when those tools come online, when the next generation of detectors starts taking data, and the waveforms start pouring in, we will finally have the chance to see whether the objects we have been calling black holes for more than half a century are really black holes at all, or whether they are something stranger, something without a singularity, something without a horizon, something held together by forces so extreme they defy imagination, sitting at the boundary of what space-time can handle, radiating violence from their surfaces without the mercy of a boundary to hide behind. The quest for proof is not just about confirming a theoretical model, it is about discovering what the universe actually built. And the universe, as we are learning over and over again, does not care what we expected. It builds what the laws of physics allow, and if those laws allow gravastars, then somewhere out there, in the depths of space, they are waiting. Dark, compact, dangerous, and undetected. For now, but not forever. The search continues, the instruments are improving, and the answer, whatever it turns out to be, is written in the gravitational waves and the light and the subtle deviations from the models we thought we understood. All we have to do is look closely enough, and when we do, the universe will tell us what it has been hiding. The quest is not over, it is accelerating. And the next chapter of this story, the chapter where we finally learn whether Einstein's equations allow for monsters even stranger than black holes, is about to begin. We have spent the last 6 chapters building a case for objects that might not exist. Gravastars, compact remnants of collapsed stars held together by dark energy cores and shells, under pressures that border on the physically impossible. Objects that look like black holes from the outside but lack the 2 features that define black holes in every textbook ever written. No event horizon, no singularity. We have talked about how they might form, what they might look like, and how we might detect them. But now we need to address the question that sits beneath all of that. What would it mean if they were real? Not for astronomy, though that would be significant. Not for astrophysics, though that would be revolutionary. But for the theory itself, for general relativity, for Einstein's equations. For the framework that has guided our understanding of gravity for more than a century. Because if gravastars exist, if we confirm them through observation, we are not just discovering a new kind of object. We are rewriting the rules. General relativity is the most successful theory of gravity ever constructed. Published by Albert Einstein in 1915, it replaced Isaac Newton's laws with a geometric description of space-time. Mass and energy curve space-time. Objects move along the curves. Gravity is not a force pulling things together. It is the shape of the universe responding to what is inside it. The equations are beautiful, compact, and extraordinarily powerful. They predicted the bending of light around the sun, confirmed by Arthur Eddington during a solar eclipse in 1919. They predicted the existence of gravitational waves, confirmed by LIGO in 2015. They predicted the expansion of the universe, confirmed by Edwin Hubble in the late 1920s, and they predicted black holes. Regions of spacetime so curved that nothing, not even light, can escape once you cross the boundary. That prediction has been tested and retested for decades, and every test has confirmed it. The shadows imaged by the Event Horizon Telescope, the gravitational waves detected by LIGO and Virgo, the orbits of stars around Sagittarius A star at the centre of our galaxy. All of it matches the black hole predictions with extraordinary precision. General relativity works, but there is a crack in the foundation, a place where the theory breaks down and admits it cannot describe what happens next. The singularity. When you solve Einstein's field equations for a collapsing star, the math drives you toward a point of infinite density and infinite curvature, a place where the equations themselves stop making sense. The singularity is not a feature of the theory, it is a failure, a red flag saying we have reached the edge of what this framework can handle. And for more than half a century, physicists have been living with that failure, hoping that someday a more complete theory, quantum gravity probably, would smooth out the singularity and tell us what really happens at the centre of a black hole. But until that theory arrives, the singularity sits there in the equations, unresolved, uncomfortable, a placeholder for physics we do not have yet. The Gravastar hypothesis challenges that placeholder. It says the singularity is not inevitable. The collapse can be halted before the density becomes infinite, and the mechanism that halts it is not some exotic new physics pulled from string theory or loop quantum gravity. It is a phase transition, a change in the state of the vacuum, something that happens within the framework of general relativity itself, using ingredients we already know exist: dark energy, negative pressure, the same force that is accelerating the expansion of the entire universe, concentrated in this case inside a collapsing star, generating enough outward push to counterbalance gravity and stop the collapse before a singularity forms. The result is an object with no event horizon, no singularity, and no breakdown of the equations. General relativity continues to work all the way through. No infinities, no failures, just a stable solution that sits at the edge of what the theory allows. That is the first profound implication. Gravastars, if they are real, do not break general relativity, they extend it. They demonstrate that Einstein's equations contain solutions we have not fully explored, endpoints to gravitational collapse that avoid the singularity without requiring new physics. The theory is richer, more flexible than the standard black hole picture suggests, and that changes how we think about what general relativity can do. For decades, the singularity has been treated as an unavoidable consequence of the theory. If you have enough mass in a small enough region, the equations say you get a singularity. That conclusion is based on theorems, rigorous mathematical proofs worked out by Roger Penrose and Stephen Hawking in the 1960s. The singularity theorems, as they are called, show that under very general conditions, collapse to a singularity is inevitable. You cannot rotate your way out. You cannot add pressure. The singularity forms. Those theorems are correct, but they are not the whole story, because they rely on assumptions, energy conditions, constraints on how matter and energy behave, and those constraints, it turns out, can be violated. Dark energy violates the strong energy condition, one of the key assumptions in the singularity theorems. The strong energy condition says that energy density plus pressure should be positive. Dark energy, with its negative pressure, does not satisfy that. And when you allow for matter that violates the strong energy condition, the singularity theorems no longer apply. The collapse is not guaranteed to reach infinite density. It can halt. It can stabilize. The Gravastar model exploits that loophole. It uses dark energy, a form of matter that general relativity already allows, to stop the collapse and avoid the singularity. The equations are still Einstein's equations. The geometry is still curved spacetime. The theory is still general relativity, but the endpoint is different. And that difference is profound because it means the singularity is not a feature of general relativity. It is a feature of solutions where the strong energy condition holds. Drop that condition, and the singularity disappears. That sounds like a technicality. It is not. It is a fundamental shift in how we interpret the theory. For decades, physicists have assumed that general relativity, when pushed to its limits, inevitably leads to singularities, places where the theory breaks and quantum gravity has to take over. The Gravastar hypothesis says that assumption is wrong. General relativity does not inevitably lead to singularities. It leads to singularities only if you assume matter behaves in certain ways. Relax those assumptions, allow for exotic states like dark energy cores, and the theory gives you different answers. Answers where the equations never break, where the curvature stays finite, where the collapse terminates in something stable. That is not a rejection of general relativity. It is a vindication. It says the theory is more robust, more complete than we thought. The singularities are not inevitable. They are optional. And nature, if gravastars exist, chose the option where the math does not blow up. But here is the uncomfortable part. We do not know whether that option is physically real or just mathematically allowed. General relativity permits a lot of solutions that do not exist in nature. Wormholes, for example. Traversable shortcuts through space-time connecting distant regions of the universe. The equations allow them. You can write down the metric, solve the field equations, and get a perfectly valid wormhole solution. But building one requires exotic matter, negative energy density, stuff that violates energy conditions even more severely than dark energy does. And we have never observed negative energy density in nature. Quantum fields can produce it in tiny amounts under very specific conditions, but scaling that up to astrophysical sizes is wildly speculative. Wormholes are mathematically consistent. They are probably not real. The Gravastar sits in a similar space, mathematically consistent, observationally untested, exotic but not impossible, and that uncertainty is what makes the stakes so high. If gravastars are confirmed through observation, if we detect gravitational wave echoes or measure a hard surface effect in an accretion disk, or see a quasi-normal mode that does not match the black hole predictions, then we learn something profound about general relativity. We learn that the theory, unaided by quantum gravity, can describe the endpoint of gravitational collapse without singularities. That is huge. It means the breakdown at the singularity is not a fundamental limit of the theory. It is a consequence of assumptions about matter that do not have to hold. And it raises the question of whether other breakdowns we worry about, other places where general relativity seems to fail, might also be avoidable if we relax our assumptions about what matter can do. Cosmological singularities, for example. The Big Bang itself is described by general relativity as a singularity, a moment of infinite density and temperature where the equations break. But if exotic matter can halt the collapse of a star, could it also halt the expansion of the universe in reverse? Could there be a gravastar-like solution to the Big Bang, a phase transition at the earliest moments that avoids the initial singularity? That is speculative. But it is the kind of speculation that becomes worth taking seriously once you have confirmed that singularities are avoidable in at least one context. The second profound implication is about quantum gravity. For decades, the singularity has been the smoking gun evidence that general relativity is incomplete. The theory works beautifully almost everywhere. But when densities and curvatures approach the Planck scale, 10 to the power of 94 kilograms per cubic meter or so, quantum effects become important. Space-time itself might stop being a smooth continuum and start behaving like something discrete, grainy, subject to quantum uncertainty. At those scales, general relativity should break down and be replaced by a quantum theory of gravity. String theory, loop quantum gravity, causal set theory, something. The singularity is where that replacement is supposed to happen. It is the place where classical physics gives up and quantum physics takes over. Confirming gravastars would change that narrative. Because if the collapse halts before the density reaches the Planck scale, before quantum effects dominate, then the singularity never forms. And the crisis point where general relativity needs to be replaced never arrives. The endpoint of collapse is described entirely by classical physics. General relativity plus dark energy. No quantum gravity required. That does not mean quantum gravity is unnecessary. It just means the singularity is not the place where we need it. Quantum gravity is still required to understand the very early universe, the first moments after the Big Bang when the entire observable cosmos was smaller than a proton. It is still required to understand black hole evaporation, the process where quantum effects near the event horizon cause black holes to radiate and lose mass. And it is still required to understand the fundamental nature of space-time, whether it is truly continuous or discrete at the smallest scales. But the singularity inside a black hole, the place everyone assumed quantum gravity would have to resolve, might not be a problem after all. If gravastars are real, the singularity does not exist. The collapse stops. And quantum gravity, whatever it turns out to be, is not needed to fix the endpoint of stellar collapse. That is a significant shift. It means the singularity is not the crisis we thought it was. It is an artifact of incomplete modelling. A consequence of assuming matter behaves in ways it might not actually behave. Fix the matter model, allow for phase transitions and exotic equations of state, and the singularity vanishes. Problem solved, without quantum gravity. But there is a twist. The gravastar model itself might require quantum effects to work. The phase transition that converts the collapsing core into a dark energy condensate is not something you can derive from classical general relativity alone. You need to understand how the vacuum behaves under extreme conditions, how quantum fields respond to intense curvature, how the energy density of the vacuum can jump from the cosmological value 10 to the -9 joules per cubic meter to something 50 orders of magnitude higher. That transition, if it happens, is a quantum phenomenon. Not quantum gravity necessarily, but quantum field theory in curved spacetime. The same framework that predicts Hawking radiation. The gravastar avoids the singularity, but it does so by invoking quantum effects before the singularity forms. It replaces one quantum problem, how to describe the singularity, with another, how to describe the phase transition. Whether that is an improvement depends on your perspective. The phase transition is less extreme than the singularity. It happens at densities we can at least extrapolate to. Using quantum field theory tools we already have, the singularity is off the edge of the map. Infinite density, infinite curvature, equations that give up. The phase transition is just barely on the map. High density, steep curvature, but finite, calculable in principle. That makes the gravastar a bridge between classical general relativity and quantum field theory. Not a full quantum gravity solution, but a hybrid. Classical geometry on the outside, quantum effects at the core. And if that hybrid describes reality, it tells us something important. It tells us that the transition from classical to quantum physics is not a sharp boundary. It is gradual. And the endpoint of gravitational collapse sits right in that transition zone, where both frameworks matter, and neither one alone is enough. The third profound implication is about new physics. Gravastars, as originally proposed by Mazur and Mottola, are built using only general relativity and known forms of matter. Dark energy, negative pressure, nothing exotic beyond what we already know fills the universe. But later studies have explored whether the gravastar idea can be extended into modified gravity theories, frameworks where Einstein's equations are replaced with something more general. F of R gravity, for example, where the Einstein-Hilbert action is modified by adding functions of the Ricci scalar, or F of R, G gravity, where you also include the Gauss-Bonnet term, or scalar tensor theories, where gravity couples to an additional scalar field. All of these are alternatives to general relativity, proposed to explain phenomena like dark energy or dark matter without invoking unknown substances. They modify the equations, they change the predictions, and in many cases, they allow for gravastar-like solutions that are more stable or easier to form than in standard general relativity. Some of these modified gravity gravastar models predict observational signatures that differ from the standard gravastar picture. Different quasi-normal modes, different surface properties, different responses to accretion or tidal forces. If we detect a gravastar and measure its properties precisely enough, we might be able to distinguish not just between a gravastar and a black hole, but between a general relativity gravastar and a modified gravity gravastar. That would be extraordinary. It would mean the detection is not just confirming an exotic object, it is confirming new physics, a deviation from Einstein's equations. Proof that gravity behaves differently than general relativity predicts under extreme conditions. That is the kind of discovery that reshapes the field. It happened in the late 1990s, when supernova observations showed the universe is accelerating, forcing the introduction of dark energy. It could happen again if gravastars turn out to require modified gravity to exist, but there is a catch. Modified gravity theories are a crowded field. There are dozens of proposals, each with its own free parameters and its own predictions, and many of them can be tuned to fit the same observations. Distinguishing between them requires precision measurements of multiple observables. The quasi-normal modes, yes, but also the mass-radius relation, the surface emission spectrum, the tidal deformability. The response to external perturbations, you need a full suite of measurements, each one precise enough to rule out alternatives. That is a tall order. And it means confirming that gravastars require new physics is harder than confirming gravastars exist. The first question is whether the objects are real. The second question is whether they fit into general relativity or demand something beyond it. Both questions are important. Both are testable. But the second one requires data quality we might not have for decades. The fourth profound implication is about what counts as a black hole. For more than half a century, astronomers have been identifying compact objects and calling them black holes. The term has become shorthand for anything with a large mass in a small volume, surrounded by an accretion disk or launching jets or bending light in ways that match the black hole predictions. But what if some of those objects are not black holes? What if they're gravastars? From a distance, the two are almost indistinguishable. Same mass, same gravitational field, same external geometry. The label black hole has been applied liberally, often without checking whether the object actually has an event horizon. Because how could you check? The horizon is a boundary in space-time, not a physical surface you can see. The only way to confirm it exists is to measure the properties of light and matter near the boundary and show they behave the way general relativity predicts for a horizon. And until very recently, we did not have the tools to make those measurements. The Event Horizon Telescope images of Messier 87 and Sagittarius A star are the closest we have come to seeing an event horizon directly. The shadow, the dark region in the center of the images, corresponds to the event horizon plus the photon sphere. The size and shape match the predictions for a rotating black hole almost perfectly. But almost is doing a lot of work. The measurements have uncertainties, the models have free parameters, and a gravastar with a surface just outside where the horizon would be could produce a shadow that looks very similar. The differences would be small at the edge of what the Event Horizon Telescope can resolve. So even those landmark images, as stunning as they are, do not definitively rule out gravastars. They constrain the possibilities. They show the object is compact, massive, and surrounded by hot gas, but they do not prove a horizon exists. Not beyond doubt. That uncertainty applies to every compact object we have catalogued. The stellar mass black holes detected by LIGO, the intermediate mass candidates in ultra-luminous X-ray sources, the supermassive objects at the centres of active galaxies. All of them are called black holes. None of them have been proven to have event horizons. The evidence is strong, the observations fit the black hole model, but fitting the model is not the same as confirming the horizon. And if gravastars are real, if they are common, then we have been mislabeling objects for decades, not because we were careless, but because we did not have the tools to tell the difference. Confirming gravastars would force a reclassification of compact objects across the board. Some would remain black holes, others would be upgraded or downgraded depending on your perspective to gravastars. And a third category, uncertain, would emerge for objects where the data is not precise enough to distinguish. That reclassification would ripple through the literature. Thousands of papers describing black hole mergers, black hole accretion, black hole demographics. All of them would need footnotes, caveats, acknowledgements that the objects might not be black holes after all. It would not invalidate the observations. The masses are real. The gravitational waves are real. The X-rays and jets and shadows are real. But the interpretation would change, and with it, our understanding of what these objects are and how they form. The fifth profound implication is about the scientific process itself. The history of physics is full of moments where a widely accepted theory was challenged by new observations and had to be revised or replaced. Newtonian gravity worked beautifully for more than 2 centuries, until observations of Mercury's orbit showed a tiny discrepancy that Newton's laws could not explain. Einstein's general relativity resolved the discrepancy and replaced Newton's framework with something more general. The new theory did not say Newton was wrong. It said Newton was incomplete, an approximation that works in most situations but breaks down in extreme regimes. General relativity is the current framework for gravity. It has passed every test we have thrown at it, but it might also be incomplete. An approximation that works almost everywhere but needs modification or extension in regimes we have not yet probed. Gravastars, if they exist, could be the signal that we are approaching one of those regimes, not because they violate general relativity, but because they push it to its limits, forcing us to account for quantum effects, exotic matter, and phase transitions that the standard black hole picture ignores. The scientific revolution that would follow a confirmed gravastar detection would not be a single dramatic shift. It would be a slow, grinding process of reinterpretation. First, the detection itself would have to be confirmed. A single anomalous waveform or spectrum would not be enough. You would need multiple detections, consistent signatures, independent confirmation from different instruments. That could take years. Once the detections were solid, the next step would be to test competing models. Gravastars, yes, but also boson stars, fuzzballs, Planck stars, and half a dozen other exotic alternatives. Each model makes slightly different predictions, and each prediction would need to be checked against the data. That process is painstaking. It requires high-precision measurements, detailed modelling, and a willingness to let the data decide rather than clinging to the model you prefer. And even once the models are narrowed down, there is the question of interpretation. Are gravastars a modification of general relativity, an extension, a special case? Do they require new physics, or do they fit within the framework we already have? Those are not questions you answer with a single observation. They are questions you answer over decades with many observations, many tests, many arguments. And yet the process would be worth it. Because the alternative is stagnation. If we assume black holes are the only possible endpoint of gravitational collapse, if we stop looking for alternatives because the black hole model fits the data well enough, then we risk missing something profound. General relativity is too successful to be completely wrong, but it is also too incomplete to be the final word. The singularities tell us that. The information paradox tells us that. The unresolved tension between general relativity and quantum mechanics tells us that. Gravastars are one way forward, one possible answer to the question of what happens when the math drives you toward infinite density and you refuse to accept infinity as the answer. There are other possible answers, other exotic objects, other modifications of the theory, but all of them require the same thing: a willingness to look beyond the standard picture and test whether nature has more options than we assumed. The gravastar hypothesis is not a fringe idea dreamed up by outsiders looking to overturn the establishment. It was proposed by serious physicists, Pavel Mazur and Emil Motola, using the equations of general relativity and the known properties of dark energy. It has been studied, extended, and refined by researchers around the world. It has been tested against gravitational wave data, X-ray observations, and theoretical constraints, and it has survived every test so far. Not because the data proves gravastars exist, but because the data does not rule them out. The observations are consistent with black holes. They are also consistent with gravastars. And until we make measurements precise enough to break that degeneracy, the question remains open. That openness, that uncertainty, is where science thrives. The gravastar hypothesis is not asking us to believe in something without evidence. It is asking us to stay open to the possibility that the evidence we have could be interpreted in more than one way. And it is pushing us to build better instruments, design better experiments, and ask sharper questions. Questions that can distinguish between a horizon and a surface, between a singularity and a phase transition, between an object that swallows information forever and an object that processes it and spits it back out. Those questions are hard. They require technology we do not have yet and precision we can barely imagine. But they are the right questions, and asking them, testing them, refusing to settle for good enough when the stakes are this high, is what moves the field forward. Einstein himself, famously, was uncomfortable with some of the predictions of his own theory. He did not believe black holes were real. He thought the singularities were mathematical artifacts that nature would find a way to avoid. He was wrong about black holes existing. The observations have confirmed that compact objects matching the black hole description are out there. But he might have been right about singularities being avoidable. The gravastar hypothesis says exactly that. Nature found a way, a phase transition, a dark energy core, a shell under unimaginable tension. The singularity never forms, the equations never break. General relativity continues to work all the way through. If that is true, if gravastars are real, then Einstein's discomfort was justified. The singularity was an artifact, not of the math, but of incomplete assumptions about what happens during collapse. And the theory, his theory, was more complete than even he realized. It contained the tools to avoid the singularity all along. We just had to look in the right places and allow for solutions we had not seriously considered. The scientific community has a long history of underestimating nature's creativity. We build models based on what we know, extrapolate them into regimes we have not tested, and assume the extrapolations are correct. Sometimes they are, often they are not. Nature does not care what we assume. It does what the laws of physics allow, and the laws of physics, it turns out, allow for a lot more than we thought. Wormholes, maybe. Time machines, probably not. Gravastars, possibly. The only way to find out is to look, to measure, to test the predictions and see whether the universe built the things the equations say it could build. That is the program. That is the quest. And it is happening right now in gravitational wave observatories and X-ray telescopes and pulsar timing arrays around the world. The data is accumulating, the sensitivity is improving, and within the next decade we will have measurements precise enough to test whether gravastars are real or just a beautiful idea that nature chose not to use. If gravastars are confirmed, the implications will ripple outward for generations. Textbooks will be rewritten, the black hole chapters will gain new sections, alternatives, exotic compact objects, gravastar physics. The singularity will be downgraded from inevitable to optional. Event horizons will lose their monopoly on the endpoint of collapse. And general relativity, the theory that has dominated gravitational physics for more than a century, will be revealed as even richer, even more flexible than we knew, not replaced, extended. The equations will stay the same, but the solutions we take seriously will expand. And with them, our understanding of what the universe can build when it pushes matter and space-time to their limits. That is the revolution waiting in the data. Not a rejection of Einstein, a vindication. His equations were right. We just had not explored all the places they could take us. And now, finally, with instruments powerful enough to see the differences and data precise enough to test the alternatives, we're ready to explore those places. To see whether the universe, in its infinite creativity, found a way to collapse stars without creating singularities, to see whether the most extreme objects we observe are black holes or something stranger, to see whether general relativity, unaided by quantum gravity, can describe the endpoint of gravitational collapse without breaking. The answers are out there, written in gravitational waves and X-ray spectra and pulsar timing residuals. All we have to do is read them. And when we do, we will finally know whether the universe's most compact objects are sealed black holes, hiding singularities behind horizons, or open gravastars, held together by forces so extreme they redefine what matter and space-time can do. Either way, the story of gravity is about to get more complicated. And the next chapter, the one where we learn what the universe actually built, is about to begin. We have spent 7 chapters building a case for objects that might redefine everything we thought we knew about the universe's most extreme endpoints, gravastars, compact remnants of collapsed stars that avoid singularities by undergoing a phase transition at the last possible moment, cores filled with dark energy pushing outward with negative pressure, shells held together by forces so extreme that calling them 10 to the power of 45 Pascals barely conveys the violence, surfaces that sit just outside where an event horizon would form, unshielded, dangerous, and ready to tear apart anything that comes close. We have explored the theory, examined the mathematics, discussed the observations, and asked whether general relativity itself needs rewriting to accommodate them. And now, at the end of this journey, we arrive at the question that matters most. What if they are real? Not just mathematically consistent, not just theoretically possible, but real, out there, right now, sitting in the centers of galaxies, hiding in binary systems, masquerading as black holes while being something fundamentally different. What does that mean for the universe? What does it mean for us? And what secrets exactly has the cosmos been keeping? Let's start with what we know, or more accurately, what we think we know. Gravastars, as proposed by Powell Mazur and Emil Mottola in 2001, are objects that form when a massive star collapses but does not form a singularity. The collapsing core reaches a critical density, and instead of continuing inward to infinite compression, it undergoes a phase transition. The vacuum state changes, the energy density jumps, and the interior fills with something that behaves like dark energy. The same mysterious force accelerating the expansion of the entire universe, but concentrated in a region smaller than a city. That dark energy core pushes outward with negative pressure, counterbalancing the inward pull of gravity. The collapse halts. And what remains is a stable, compact object with no singularity, no event horizon, and no breakdown of the equations. Just a boundary. A thin shell separating the dark energy interior from the curved space-time exterior. A shell under pressures so extreme that neutron star cores look gentle by comparison. A shell that is not a horizon, not a one-way membrane, but a physical surface where matter can hit, reflect, and interact. That is the gravastar, and if it exists, it solves problems that have plagued theoretical physics for more than half a century, while introducing dangers we never had to worry about with black holes. The danger is not the singularity. Gravastars do not have singularities. The danger is the surface. Because a black hole, for all its fearsome reputation, hides its violence behind an event horizon. The singularity is sealed off, causally disconnected from the rest of the universe. You cannot reach it without crossing a boundary that guarantees you will never escape. And for a supermassive black hole, the kind that weighs billions of solar masses, crossing that boundary is smooth, gentle even. The tidal forces at the horizon are weak. You would not feel a thing. The violence comes later, deeper inside, where the tidal forces grow and eventually rip you apart. But the horizon itself is safe. It is geometry, not a physical barrier. A gravastar has no such protection. The surface is right there, exposed to the universe, with gravitational forces strong enough to shred anything that approaches. The tidal forces do not wait until you cross some invisible line. They start immediately, escalating as you get closer, pulling harder on your feet than your head, stretching you into a shape that flesh and bone were never meant to hold. And you are still outside the radius where a black hole's horizon would be. Still in what should be the safe zone. But with a gravastar, there is no safe zone. Just a surface, infinitesimally thin, held together by forces that make space-time itself groan under the strain. And every meter closer makes it worse. That is the first secret the universe might be hiding. The most compact objects we observe, the things we have been calling black holes for decades, might not have horizons. they might have surfaces. And surfaces, as it turns out, are far more dangerous than horizons ever were. Because a horizon is passive. It does not reach out, it does not grab, it just sits there, waiting for you to cross it, and once you do, the geometry ensures you cannot leave. A surface is active, it reflects, it absorbs, it radiates. When matter hits a gravastar surface, the impact releases energy. The shell vibrates, emitting gravitational waves. The matter compresses, heats, and converts into radiation that escapes. The gravastar processes what falls onto it and spits out the remains. That interaction, violent and immediate, is something black holes do not do. Black holes swallow, gravastars chew. And the difference, subtle as it sounds, changes everything about how these objects behave and what happens to anything unlucky enough to get close. Now consider the implications if gravastars are common. Not rare, exotic objects sitting in some corner of parameter space where conditions have to be just right, but common. The default outcome of stellar collapse under conditions that are not as exotic as we assumed. If the phase transition happens naturally, if the vacuum really does condense into a high-energy density state when space-time curvature gets steep enough, then gravastars could be everywhere. Every stellar mass black hole candidate we have detected with LIGO might be a gravastar. Every supermassive black hole candidate at the centre of a galaxy might be a gravastar. Every X-ray binary, every active galactic nucleus, every gamma-ray burst powered by what we thought was a collapsing star forming a black hole. All of them could be gravastar formation events instead. The observations would look the same, the masses would match, the gravitational waves would fit, the light bending, the accretion disks, the jets, all of it consistent with both models. We have been cataloguing these objects for decades, calling them black holes, and never checking whether they actually have event horizons. Because how could we check? Until very recently, we did not have the tools, but the tools are coming. Gravitational wave detectors sensitive enough to resolve the ring-down phase and see whether the quasi-normal modes match a black hole or something else. X-ray observatories precise enough to measure the hard surface effect, the slight excess emission that comes from matter hitting a physical boundary instead of disappearing through a horizon. Pulsar timing arrays capable of detecting nanohertz gravitational waves from supermassive binaries and testing whether the waveforms show echoes or frequency shifts that do not fit the black hole model. Very long baseline interferometry networks that can image the shadows of compact objects with enough resolution to distinguish between a horizon and a surface. All of those tools are being built. Some are already online, and within the next decade we will start getting answers. Not guesses, not models, answers. Data precise enough to test whether the objects we have been calling black holes are actually black holes, or whether some, maybe most, maybe all of them, are gravastars. And if the answer is gravastars, then the universe has been lying to us. Not maliciously, but by presenting objects that look like black holes from a distance while being something fundamentally different up close. The lie is not in the observations. The observations are real. The masses, the gravitational fields, the light bending, all of it accurate. The lie is in the assumption that those observations can only be explained one way, by objects with event horizons and singularities. We assumed that because the standard model of stellar collapse, the one built on general relativity and decades of careful work, predicted black holes, and the observations fit. So we stopped looking for alternatives. We catalogued the objects, measured their properties, and moved on. The gravastar hypothesis is asking us to go back, to re-examine those catalogues and test whether the objects inside them are what we thought they were. It is not saying we were wrong, it is saying we might have been incomplete. And incompleteness in science is an invitation, an open door, a chance to learn something new. The philosophical implications are staggering, because if gravastars are real, then the universe has found a way to cheat death. Not metaphorically, literally. The standard story of stellar collapse is a tragedy. A massive star runs out of fuel, the core collapses, and the endpoint is a singularity, a place where the laws of physics break down and everything that falls in is lost forever. The singularity is the ultimate death. No escape, no reversal, no hope. It is the place where matter goes to stop being matter, where information goes to be destroyed, where the equations give up and admit they cannot describe what happens next. The gravastar story is different. The collapse halts. The core transitions into a new state, a dark energy condensate, and the structure stabilizes. No singularity forms. The equations keep working. The object exists in a stable equilibrium, held up by its own internal pressure, and it can sit there indefinitely, forever potentially. The gravastar does not die, it transforms. And that transformation, if it is real, means the universe has an escape hatch, a way out of the singularity trap that we thought was inevitable. That raises questions we're not used to asking in astrophysics, questions that sound more like philosophy or theology than science. What does it mean for an object to cheat death? What does it mean for the universe to contain endpoints that are not final? If a gravastar can exist indefinitely, stable and unchanging, does it have a future? Can it evolve? Can it interact with its surroundings in ways that change what it is? Black holes are simple. They have three properties: mass, charge, and spin. That is it. Everything else is erased. The no-hair theorem, one of the cornerstone results of black hole physics, says that black holes forget everything about their past except those three numbers. You cannot tell whether a black hole formed from a collapsed star, or from compressed gas, or from exotic matter. All the details are lost. Gravastars, by contrast, have structure, a core, a shell, a boundary between them. That structure encodes information about how the gravastar formed, what conditions were present during the collapse, what equation of state describes the shell. The gravastar remembers, and if it remembers, it is not just a mass sitting in space. It is an object with history, with properties that depend on where it came from and how it got there. That makes gravastars more complex than black holes, more interesting, and potentially more dangerous, because complexity means unpredictability. A black hole is stable. Once formed, it sits there, unchanging, until Hawking radiation slowly saps its mass over timescales longer than the current age of the universe. Gravastars might not be stable. The shell is under enormous tension. The dark energy core is in an exotic vacuum state. If the balance between the two is disturbed, if the shell weakens or the core destabilizes, the gravastar could collapse into a black hole. Or it could explode, releasing the energy stored in the shell and the core in a burst that rivals a supernova. We do not know which would happen because we have never observed it. The models give different answers depending on the parameters. Some predict stability. Others predict decay, and the timescale for that decay, if it happens, could be anything from microseconds to trillions of years. A gravastar that looks stable today might not be stable tomorrow, or it might be stable for longer than the universe has existed. We do not know, and that uncertainty is unsettling. Now layer on top of that the possibility that gravastars are not just stable compact objects sitting quietly in space. They might be active, dynamic, interacting with their surroundings in ways that produce observable effects. Consider accretion. A black hole accretes matter smoothly. The gas spirals inward, crosses the event horizon, and disappears. The process is steady, predictable, and well modelled. A gravastar accretes differently. The matter spirals inward, but when it reaches the surface, it does not disappear. It hits. The impact releases energy. The surface heats. The shell vibrates. And depending on how the shell responds, the gravastar might emit bursts of radiation every time a significant amount of matter lands on it. Those bursts could be periodic if the gravastar is rotating and the accretion is uneven. They could be stochastic if the accretion is chaotic. Either way, the light curve, the pattern of brightness over time, would be different from what a black hole produces. And if we could measure that light curve precisely enough, we could use it to test whether the object has a surface or a horizon. Then there are the jets. Many compact objects launch jets, narrow beams of plasma and radiation that shoot outward at nearly the speed of light. The jets are powered by magnetic fields threading through the accretion disk and anchored in the compact object's spin. For black holes, the mechanism is well understood. The Blandford-Snayak process extracts rotational energy from the black hole and channels it into the jet. For gravastars, the mechanism is less clear. The magnetic field lines cannot thread through an event horizon that does not exist. They thread through the surface instead. And the surface, with its extreme tension and physical boundary, interacts with the magnetic field in ways a horizon does not. The result could be jets that are more powerful or less powerful or structured differently. The differences would be subtle, but they would be there. And measuring them could provide another test, another way to distinguish between the two models. The danger, though, is not just in the uncertainty. It is in what happens if we are wrong about what these objects are. Imagine a mission to explore a compact object. A probe sent to orbit close to what we think is a supermassive black hole, measuring the space-time curvature, testing general relativity, searching for signs of the event horizon. The mission is designed with the assumption that the object has a horizon, that the tidal forces at the horizon are weak, that the probe can orbit safely at a distance of a few gravitational radii and send back data. But if the object is a gravastar, those assumptions fail. The tidal forces are stronger than expected, the surface is closer than the horizon would have been, and the probe, instead of completing its mission, gets torn apart. Not because we made a mistake in the engineering, but because we made a mistake in the model. We assumed the object was one thing when it was actually another. That is the practical danger of misidentifying gravastars. The theoretical danger is deeper. It is the danger of building an entire framework, an entire understanding of how the universe works, on top of objects we have misidentified. Every calculation of black hole demographics, every model of galaxy formation that relies on supermassive black holes at the centers, every simulation of black hole mergers, every estimate of gravitational wave event rates, every prediction of what we should see when we point our telescopes at the sky. All of it assumes the objects are black holes. If they are gravastars, the numbers change, the rates change, the predictions change, and we have to go back and redo the work. Not all of it. The masses are still real. The gravitational effects are still real, but the interpretation shifts, and with it, our understanding of the processes that shape the universe. There is also the possibility that gravastars are rare, that they form only under specific conditions in a narrow range of masses or spins or metallicities, that most compact objects are black holes, but a handful scattered across the cosmos, are gravastars. If that is the case, then confirming gravastars does not upend everything. It adds a footnote, a new category of exotic compact objects that exist alongside black holes, neutron stars, and white dwarfs. The universe's zoo of endpoints gets a little more crowded. That would still be significant. It would still mean singularities are not inevitable, that the vacuum can condense into high-energy states under extreme curvature, that general relativity contains solutions we had not fully explored. But it would not be a revolution. It would be an expansion, a refinement, and the practical impact for most of astrophysics would be minimal. We would keep studying black holes because most of the objects we observe would still be black holes. The gravastars would be curiosities. Interesting, yes. Important for understanding the theory, absolutely, but not central to the story of how galaxies evolve or how the universe expands. But what if gravastars are not rare? What if the phase transition happens easily, naturally, whenever a collapsing core reaches the right density? What if every stellar mass compact object more massive than about 3 solar masses is a gravastar, not a black hole? What if every supermassive object at the center of a galaxy is a gravastar? That changes everything. It means we have been wrong about the nature of compact objects for decades. It means the singularity, the feature we thought was inevitable and unavoidable, never actually forms. It means the event horizon, the boundary we thought was a fundamental feature of collapsed objects, does not exist. And it means the universe has been operating under rules we did not fully understand, producing objects we misidentified, hiding a secret so profound that confirming it would reshape the field. That is the dangerous possibility. Not dangerous in the sense of physical harm, though gravastars are certainly dangerous in that sense too. Dangerous in the sense that it forces us to admit we missed something big, something that was there all along, hiding in plain sight, waiting for us to look closely enough to see the difference. The ongoing scientific frontier, the search for proof, is accelerating. Every year, gravitational wave detectors get more sensitive. Every year, X-ray observatories collect more data. Every year, pulsar timing arrays add more pulses to their datasets and improve their timing precision. The tools are improving, the measurements are getting sharper. And the tests, the ones that will finally tell us whether gravastars are real or just a beautiful theoretical idea that nature chose not to use, are coming. Some of them are already here. The gravitational wave signals from LIGO and Virgo are being analysed for echoes, faint repeating pulses that would indicate a surface instead of a horizon. The X-ray spectra from accretion disks around compact objects are being modelled to test for the hard surface effect. The shadows imaged by the Event Horizon Telescope are being compared to predictions for both black holes and gravastars. None of these tests have given definitive answers yet. The differences are small, the noise is large, but the sensitivity is improving. And within a decade, we will have data clean enough and precise enough to break the degeneracy, to see whether the objects are black holes or gravastars or something else entirely. And when that answer comes, when we finally know what these objects are, the universe will reveal its most dangerous secret. Not that gravastars are more violent than black holes, though they are. Not that they produce stronger tidal forces or hotter accretion disks or stranger jets, though they might. The secret is that the universe, at its most extreme, does not do what we expected. The singularity, the place where our equations break and our understanding fails, might not exist. The event horizon, the one-way boundary that defines a black hole, might be an illusion. A consequence of assuming matter behaves in ways it does not actually have to behave. And the objects we have been studying, cataloguing and calling black holes might be something fundamentally different, held together by forces we barely understand, radiating violence from their surfaces without the courtesy of a horizon to hide behind, sitting at the edge of what general relativity allows, where classical physics meets quantum effects and neither framework alone is enough. That is the secret. And if it is true, then the universe is stranger, richer, and more dangerous than the story we have been telling for the last 50 years. The ethical questions, the ones that sound out of place in a discussion of compact objects and gravitational physics, are worth confronting. Because if gravastars are real, if they represent a stable endpoint where collapse halts and the structure persists indefinitely, then we're talking about objects that cheat death in a way nothing else in the universe does. Stars die, galaxies fade. Even black holes over unimaginable timescales evaporate via Hawking radiation. But gravastars, if they are stable, do not. They just sit there, forever, held up by their own internal pressure, monuments to the moment when collapse was supposed to continue but did not. That permanence is unsettling. It raises the question of whether there are other places in the universe where the rules allow for escape hatches, where processes we thought were inevitable turn out to be avoidable. If stellar collapse can be halted by a phase transition, can other catastrophic processes be halted too? Can the expansion of the universe, driven by dark energy, be reversed by some future phase transition? Can the heat death of the cosmos, the slow fade into thermal equilibrium that thermodynamics predicts, be avoided by structures that generate their own energy indefinitely? These are speculative questions, but they are the kind of questions that confirming gravastars forces us to ask. Because if the universe found one way to cheat the rules, it might have found others. The sense of wonder that comes with this line of inquiry is profound. We live in a universe that is billions of years old, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. And despite all that scale, despite all the observations we have made and the models we have built, we're still discovering that the universe has tricks we did not anticipate, objects we misidentified, processes we misunderstood, endpoints we thought were final that turn out to be stable. The gravastar hypothesis, whether it is confirmed or ruled out, is a reminder that the universe does not owe us simplicity. It does not owe us answers that fit neatly into the frameworks we have built. It just is. And our job, as scientists, as observers, as beings trying to make sense of the cosmos, is to look closely enough, measure precisely enough, and think carefully enough to see what the universe actually built. Not what we expected it to build, what it built. The apprehension, the unease that comes with that wonder is also real. Because every time we look more closely at the universe's most extreme objects, we find something that challenges our intuitions. Neutron stars, where matter is compressed so tightly that atomic nuclei merge into a soup of quarks and gluons. Black holes, where space-time curves so steeply that not even light can escape. And now, potentially, gravastars, where the vacuum itself condenses into a state with energy densities 50 orders of magnitude higher than the cosmological norm, held together by shells under pressures that make the center of a neutron star look like a gentle breeze. Each discovery pushes the boundaries of what we thought was possible, and each boundary, once crossed, reveals new ones waiting beyond. The gravastar is not the endpoint. It is another step, another piece of the puzzle, And the puzzle, as far as we can tell, does not have a final piece, just more questions, deeper mysteries, stranger objects waiting to be found. The universe, it seems, is not running out of surprises, it is accelerating into them. Every new detector we build reveals phenomena we did not predict. Every new observation refines our models and exposes gaps we did not know were there. The gravitational wave detections showed us black hole mergers at rates higher than expected. The Event Horizon telescope images showed us shadows that matched the predictions almost perfectly, but with just enough wiggle room to allow for alternatives. The pulsar timing arrays are starting to see a nanohertz gravitational wave background that could come from supermassive black holes or supermassive gravastars or something we have not thought of yet. And the next generation of instruments, the ones that will come online in the 2030s and beyond, will see even more. They will measure the ring-down frequencies of merging compact objects with enough precision to distinguish between black holes and gravastars. They will image the shadows of supermassive objects with enough resolution to see whether the boundaries are horizons or surfaces. They will detect gravitational wave echoes if they exist, and use them to map the internal structure of the most compact objects in the universe. And when those measurements come in, when the data is analysed and the models are tested and the alternatives are ruled in or out, we will finally know, not guess. Know. And if the answer is gravastars, if the data confirms that some or all of the objects we have been calling black holes are actually something else, then the next question becomes obvious. What else are we wrong about? What other assumptions have we been making for decades or centuries that seemed safe at the time but turn out to be incomplete? The history of science is a history of overturned assumptions. The Earth is not the centre of the solar system. The solar system is not the centre of the galaxy. The galaxy is not the centre of the universe. Space and time are not absolute. They are relative, woven together into a single fabric that bends and stretches and ripples. Matter and energy are equivalent, interchangeable under the right conditions. The universe is expanding, and the expansion is accelerating. Each of those discoveries forced a revision, a rewriting of the textbooks, a rethinking of the questions. The gravastar, if confirmed, would be another entry on that list. Another moment when we looked closely and realised the universe was not what we thought. And each of those moments, unsettling as they are, is also a triumph. Because it means we are getting closer, not to a final answer, there might not be one, but to a more complete picture, a deeper understanding, a model that fits the data better and makes fewer assumptions. The future of astrophysics, if gravastars are real, is both more complicated and more exciting. More complicated because every model that assumes black holes will need to be revisited. Every simulation, every demographic study, every prediction, all of it checked against the possibility that the objects are gravastars instead. That is a monumental task. It will take years, maybe decades to work through. But it is also exciting because it means there is more to discover, more structure to explore, more physics to understand. Gravastars are not just black hole substitutes, they are new objects with new properties. They have cores, they have shells, they have surfaces that interact with the universe. They radiate differently, they accrete differently, they merge differently. Understanding all of those differences, mapping out the parameter space, testing the models against observations, is a research program that could occupy the field for the next century. And every step of that program brings us closer to understanding what the universe actually built when it collapsed massive stars and let gravity do its work. The sense of apprehension, the unease, comes from the recognition that the universe is vast and we are small. Our models are approximations, our observations are limited, our understanding is incomplete. And every time we think we have figured something out, every time we think the picture is complete, the universe shows us something new, something we missed. Something that was hiding in the data all along, waiting for us to look closely enough to see it. The gravastar is one of those things. An object that might have been there for billions of years, sitting in the centres of galaxies and binary systems, masquerading as black holes, and we never noticed because we did not have the tools to tell the difference. That is humbling. And it is a reminder that the universe does not reveal its secrets easily. It makes us work for them. It makes us build better instruments, ask sharper questions, and test our assumptions over and over until we are sure. And even then, even when we think we are sure, there is always the possibility that we are wrong, that the next observation will show something we did not predict, that the model will need another revision, that the story is not over, but that is science, that is the process, and it is the only process we have that reliably gets us closer to the truth. Not by leaps of intuition or flashes of genius, though those help, but by careful measurement, rigorous analysis, and a willingness to follow the data wherever it leads, even if it leads to objects we did not expect, even if it forces us to admit we were wrong, even if it means rewriting the textbooks and starting over, because the alternative is stagnation, clinging to models that fit the old data but do not fit the new, refusing to ask whether the objects we've been calling black holes might be something else, settling for good enough when the stakes are too high to settle. The Gravastar hypothesis is not asking us to believe in something without evidence. It is asking us to stay open, to keep testing, to build the instruments and make the measurements and see what the universe tells us, and when the universe tells us, to listen. The most dangerous secret the universe might be hiding is not that gravastars exist. It is that we almost missed them. That we came within a few years, a few technological advances, a few careful observations, of locking in the black hole model as the final word and moving on. If the gravitational wave detectors had not been built, if the sensitivity had not improved, if the theorists had not kept exploring alternatives and pushing the boundaries of what general relativity allows, we might have missed the gravastar entirely. We might have catalogued thousands of compact objects, called them all black holes, and never realized that some of them were fundamentally different. That near miss, that possibility, is what makes the search so urgent, because the universe does not wait for us to catch up. It does not hold its secrets in reserve until we are ready to understand them. It just is. And if we do not look, if we do not measure, if we do not test, we will never know what we missed. So here is where we stand, at the edge of a discovery that could reshape our understanding of the universe's most compact objects. Gravastars might be real, they might be common, they might be sitting in the centers of galaxies, in binary systems, in gamma-ray burst remnants, and in every supernova we observe. Or they might be rare, confined to a narrow slice of parameter space where the conditions are just right. Or they might not exist at all. The phase transition might not happen. The dark energy core might not form. The shell might not stabilize. And the singularity, with all its problems, might be the true endpoint after all. We do not know, but we are about to find out. The instruments are being built. The observations are being made, the data is accumulating, and within the next decade, possibly sooner, we will have measurements precise enough to test the models and see which one matches reality. That test is coming. And when it arrives, when the gravitational wave echoes are detected or ruled out, when the X-ray spectra show a hard surface effect or do not, when the pulsar timing arrays resolve individual supermassive binaries and measure their waveforms with enough precision to distinguish between horizons and surfaces, we will finally know. The universe will tell us whether it built gravastars, whether it found a way around the singularity, whether the objects we've been calling black holes for more than half a century are really black holes or something stranger. And if the answer is gravastars, if the data confirms them, then the universe's most dangerous secret will be unveiled. Not that these objects are more violent than black holes, though they are. Not that they produce stronger tidal forces or stranger jets, though they might. But that the universe, in its infinite creativity, found a way to build compact objects that avoid singularities, avoid event horizons, and sit at the boundary of what general relativity and quantum field theory can describe. Objects held together by dark energy cores and shells under pressures that defy imagination. Objects that cheat death, that transform instead of collapsing, that exist in stable equilibrium without the breakdown of the equations. Objects that are, in every measurable sense, more dangerous than the black holes they replace because they lack the one feature that made black holes safe. The event horizon, the boundary that hides the violence inside. Gravastars have no such boundary. The violence is on the surface, exposed, immediate, and waiting for anything that comes too close. That is the secret. That is the danger. And if it is real, then the universe has been hiding it in plain sight for billions of years, waiting for us to build the right instruments, ask the right questions, and look closely enough to see the difference. The quest is not over. It is accelerating. And the answer, whatever it turns out to be, will be written in the gravitational waves and the light and the data streaming in from observatories around the world. All we have to do is look, And when we do, the universe will tell us what it built. The most dangerous secret is not that gravastars exist, it is that we are finally ready to find them. And once we do, nothing about the story of gravity, space-time, or the fate of collapsing stars will ever be the same. The future is waiting, the instruments are ready, and the universe, patient as always, is about to reveal whether the objects at the edge of everything are black holes or something far, far stranger. The search continues. And the next chapter, the one where we finally learn the truth, is about to begin. Here is where we leave it, not with certainty, but with a question sharper than any we started with. If gravastars are real, if the universe found a way to halt collapse before the singularity forms, then the objects we have been cataloguing for decades, the ones we pointed at and confidently labelled as black holes, might be something fundamentally different, not holes at all. Not voids where matter vanishes and information dies, but surfaces, physical boundaries under pressures so extreme they make neutron star cores look like open air, held together by forces we barely understand, sitting at the exact radius where a horizon should have been but is not. No singularity to hide the breakdown, no horizon to shield the violence, just a boundary, exposed, immediate, and far more dangerous than anything we thought we were looking at. That possibility, uncomfortable as it is, should excite you, because it means the universe still has moves we have not seen, tricks we have not anticipated, solutions to problems we thought were unsolvable, written into the equations all along, waiting for us to look closely enough to find them. The singularity is not inevitable. The event horizon is not guaranteed. And the story of what happens when a massive star collapses, the story we've been teaching for more than half a century, might need a final chapter we never wrote. The instruments are improving, the data is accumulating, and within a decade, maybe less, we will have measurements precise enough to see whether the universe built what we expected, or whether it built something stranger. The answer is out there. Written in gravitational waves, in X-ray spectra, in the faint echoes of objects colliding at the edge of space-time, all we have to do is listen. And when the universe speaks, when it finally tells us what sits at the centres of galaxies and the remnants of collapsed stars, we will learn whether the most extreme objects in existence are sealed pits hiding singularities, or open blades radiating violence from surfaces we never knew were there. Either way, the universe wins. It always does. Because it does not care what we expected. It built what the laws allow. And those laws, it turns out, allow for far more than we thought. The quest is not over. The mystery deepens, and the most dangerous secret the